a bad question. For the first one here.
Jesus. One sec. Well, what about it?
Yeah, yeah. Is superposition the best way to solve this,
Just
or only way?
do
Because this is how that's what we did in class.
superposition.
Yeah,
Mm,
superposition, where you like get rid of one of the voltage sources.
find VO? No, just solve it like you just solve it the way we solve all the op-amp problems. We will like figure out the voltages at the nodes at A, and then we figure out the other voltage, the positive node.
Yeah, but
You know how we always done it?
how do you do that? Yeah. But
What do
like,
you mean?
but there's voltage. There's two voltage sources. How do you find the voltage at A then?
It's just 10 millivolts
What
minus
do you mean? What about the A one?
that
Can you
one.
do that?
Yeah, because
You
it'll give
sure?
you what is the equation? It's oh my god, I'm trying to remember. VI will be plus minus the V plus minus the V minus you get it there. Like, let me see. No, I have,
Oh,
what is it asking for? I'm V. Oh, you just do it using.
VO.
You do it using. Yeah, you
I was just gonna do superposition because that's what we did in class like a few weeks back now.
superposition. So you get rid of the volts.
Yeah,
Really?
you get rid of one voltage source, you
Huh.
solve for VO, then you get rid of another voltage source and solve for VO again using KCL. And then you add those voltage sources together.
Oh, that would work. I didn't know you did. Never done
Yeah,
it.
I don't know. That's the only way I knew how to do it. That's why I'm like, is that the best way to do it? I don't know. Actually,
Let's
let me go
see.
back to what we did in class. I want to see if adding them together would actually be the exact same or not.
It would be. That is how superposition works.
Oh,
That is like the theory. It should add up to what you need. VO.
so I don't like I don't like any of this.
Wait, but I never done it. But it works.
Mm.
When I would solve it like this. I would find the currents going into the.
Well, technically, okay. So if this were the case, right, my VO would be equal to 8 plus 10.
Yeah.
Okay, so that
Sorry.
ain't right
Say it
though.
again. Wait, say it again.
That ain't
That's
right.
what's not right.
So what would my VO be if I had the VA then?
Mm,
Wouldn't VO be equal to VA or no? Well, maybe not.
mm-mm. It would not. But wait. I remember. So you find the currents in, and then we saw. Well, oh, because VO was just straight up the. Wait. We do. I thought we saw where the voltage. That's that'll be not inverted. V1. So the thing is, the voltage eight minus whatever the voltage at VA is will equals 0. So that will give you VA, and then you do voltage division. Yeah, wait. I think where's my calculator? Let's see. But you can also do some. I don't want to be 8 minus the VA voltage, which would be. So that means that at VA it's also 8. And then you do. mm, I'll just do the first. I think we have to do it first. Which one is it? I think this. Let's see. I'll do this one really
We're good.
just to see if it works.
Huh? Yeah, write out the question. Just do this one with us. Yeah. I know. They do that in the neighborhood.
Okay.
Might be my dad. Probably is. Not bad.
Oh, what's I guess. Wait, do you have the answer or no? Question?
I do not have the answer for this question. I know we did this same thing for
I
other
see.
homework, but you know, just let me pull it up really quick. Uh, Op amps.
Yeah.
Matty Patrick, do you guys remember where we did this? I mean, this is. I'm just remembering. I'm trying. Yeah, no, I'm trying to figure out where we did it in the lecture.
Oh, it's that one. You just skipped over
Yeah,
it.
it was that one. I know, but that one doesn't have any notes or anything like that. It's fine. I know
Oh,
we did one with it. That's why I'm saying that.
wait, is this wait, I just realized this is something now.
It's fun now.
See.
This is the wrong lecture. Let me find it. What are you guys doing? I find the email where she sent the thing. Oh, well, that's no. I'm not looking for that one. I'm looking for something else. I'm looking. Where did we do this?
Where's my summing
Maybe
up?
she didn't post it. That's funny.
Mm,
Hmm.
difference. What do you mean? Wait, where's my
I
oh
don't think she
summing?
posted her notes.
Oh, it's not the same configuration.
Yeesh. Oh,
How you would do it?
two sources, right? Two sources, yeah. She didn't post her notes on it. So. She did one. I don't know. Yeah, I know. That's what I'm saying. I have it right here. 6 volts and 4 volts, right? Hmm. Patrick, do you have your notes on this? I can check my practice. I can't check anything on my computer. Oh yeah. My notes are bad because she wrote a bunch of stuff on my notebook and I just never erased it. It's similar to this thing. That's another. Bruh. I don't like op amps.
Oh,
Yeah.
here, this is how it goes. At so VB, you have the ideal equation. B, you know that VB is equal to volts, meaning that this just gives you no VA. We apply PCO at the one. Thing is though, good ideal, no currents, which is why the current only flows upward. So we're
Mhm.
gonna solve for one. I will just here this notable to 10 minus 8 over 4, right? See it?
Mhm.
I'm doing 10 millivolts minus the VA. VA 4. We know that VA is 10 millivolts. That's the current. Now that we know that, we also know. Oh, but then to solve for the voltage, we could just do 2 times the I. We know that VO is
Mhm.
that's what I got. That's how I would do it.
1 volt.
Is 1 volt. Because that's how you solve it ideally.
So hold on. Let me zoom in.
Actually, she said don't use any formulas.
Yeah, she said no using formulas. But what did you do?
Hmm.
Yeah, I wanted to. But you have another. Okay, what happens with the other source voltage, the 8 millivolts? How'd you do that?
I just said equal to VB. That's
You
VB.
have
So
VB
I
is equal to
find
that, yeah?
yes, and then you use the equation. That's it, which is the ideal equation
Oh,
for
it's
an
an
op amp.
auxiliary equation. But why are they equal? I mean,
What do
okay,
you
no,
mean?
I mean, I get why they're equal. I get why they're equal. But shouldn't VA be equal to 10 millivolts or something like
No,
10
VA would
millivolts?
be VA is here,
Yeah. What about the 10 millivolts?
right here.
Yeah.
There's a resistor. It like separates
Yeah.
it.
Yeah.
You know
There's
what I mean?
still yeah, but shouldn't VA be like the sum of the voltages or something then?
What about this volt? Then you have to consider the voltage here too, as well. If you don't know. Oh, I'm
Yeah.
sorry, not that one. This one, my bad. This one, which is VO. This will be VO here.
Yeah.
This is VO. So if you wanted to do, you're saying just doing through like the voltage sums.
I don't know.
Mm,
uh okay, so you said VB is equal to VA, right?
yeah, just because of this equation,
Sure. And then you said that VA is equal to 8 millivolts because of that.
because of this equation, yeah, because VV is equal to I should have wrote that. Because VV is equal to 8.
Yeah. But then why doesn't the 10 millivolts have any effect on the VA?
Mm,
That's my question.
because how to explain it? If we do it in terms of the voltage drop, for example, it does, but it's not 10. Ah, Wait,
It's not 10. There would be a voltage drop because of the resistor, but
yeah,
like there would still be a value. It would still affect it, wouldn't it?
but it would affect the current,
Yeah, it would
not
affect the current.
the voltage at VA.
What?
Trying to think of words how to explain this. 'Cause I just mm, anyone have any ideas? Anyone's allowed to speak up if they want to. I can't think of a way to explain it. Maybe we could do KVA wave. 2, because we know VO is 7 minus 10 plus 8, 2 plus 1 is 0. Yeah, minus 10. Yeah. Wait, that way. So look, we do KVA. This is then this will be another. Well, that still doesn't answer your question. I don't know how to explain it. It doesn't affect it. It affects it indirectly it affects the current, not what the voltage is at VA. Because we know VA because of the ideal op amp. We can't get VA otherwise. There's no other way. You know what I mean? Because if we didn't know VA here, then it would just do like the current would just be I equals 10 millivolts minus VA over 4. Like you have to solve it some other way. The 10 isn't affecting VA, but it affects the voltage drop through the resistor. Indirectly, it does, right? I guess because if it was 0, then VA would be different.
I just
So
don't
I
like
guess
that
you were
VA
right.
is completely equal to the 8 millivolts. I guess
You
what
don't
I
like
don't
that?
like. Well,
But
wait,
that's just
what if there was
hmm.
no 4 kilo ohm resistor?
What if there was no what?
4 kilo ohm resistor.
Then VA would just be it still wouldn't just be 10 because you still have to consider
Well, yeah, it wouldn't be 10, but I'm saying it wouldn't be like the sum or something like that.
if
They're
there's
both going to the same node.
if this is gone.
Yeah.
And then you're saying VA would be what?
I don't know, like 8% or something like that.
Mm-mm.
There's no the current is 0. Get that.
Oh yeah. Also, you have a short, so there would be no voltage drop.
Yeah, there would be no voltage drop.
It would be the same. Oh, this will be 10. This will all be 10, and then this will also be 10.
Wait, what happens to the 8 millivolts then?
But now we have a problem. Actually, it might be just 2 minus 10 plus 8. How would you write that?
Now you're saying it's the sum of it.
No, wait. You're right though. How would you write that?
I don't know.
I don't know. Should ask Suarez that question. What happens if there's no resistance? What do you mean, Like, what? Bro, email her. She'll respond to you like 2 minutes. Screenshot the question, ask her, like, what happens if there's no resistor?
Spring break, man. She's definitely not going to respond to me.
Alright, I'll ask her then. We have to do first order. I can't waste time on op amps. And then I have to do second orders. I'm sorry. Maybe later. I'll like look it up and I'll chat GPT and then see if I can figure an explanation for you.
Okay. I don't like this question. This is like the first question on the practice exam. That's why I'm asking.
Oh, okay. I also plan on reviewing the practice exam. All the questions. I wasn't prepared for an op amp, so I didn't do research.
Yeah.
Okay. After. All right, wait. We're gonna start off with this one.
Okay.
This is a first order problem. Yeah. So this is not on the exam. This is
Not on the
T1.
Okay.
I do have is after. Okay. So we know that for steady states past conduct. Right, so these are important things to keep in mind. We also have the equations over here.
Yeah.
F2 dot. We're going to do the first thing, which is let me see. switch says. Subset finite switch over here. So the switch has been closed on for a long time. So at T, at T, do that. Actually, one more thing. We also know that for capacitor and inductors, since they're storage element devices, they don't change instantaneously.
Mhm.
So, for example, capacitor at 0 minus, its voltage at before the switch is closed down or open. It doesn't matter. It just depends what the state of the switch is. It'll be the same voltage the next state, and it'll be again voltage. This goes for the same for an inductor. Said it's they're storage element devices, so their properties can't change instantaneously. Keep those in mind.
Yeah.
Okay, so now we have this.
Will you post it, upload it to the chat?
Yeah,
when
I'll
you're
upload
done?
everything.
Yeah.
Mhm.
Okay, thank you.
Wait, is Patrick recorded for this? I should tell him.
Yeah, Patrick, you're recording it.
Go.
Yeah, he's recording.
Some of the audio issues are prevalent
What do you mean by that?
because occasionally with the Wi-Fi it's cutting out.
Sure.
Uh, is what's the
Oh.
Alright, this is different. I'm gonna have to add more. Talking about current.
Isaac, by the way, your mic's a little choppy.
Is it really?
Yeah.
Okay. My suppression. Or change the gain on it. How's it now? Or let me know if I keep cutting out.
Yeah, I got you.
Thank you. Switch. Let's close at less than 0. Okay. And before I move on, let me grab everything now. Yeah. All right. So for resistor, what I said here does not apply because resistors aren't storage element devices, meaning that their what do we call it, power or like charge that they hold can change instantaneously. Meaning like if it's 2 volts before the switches open up, that means it can change to like 8 volts when the switch closes down, something like that.
Mhm.
This means that you have to do a bit more work because these things like reduce the amount of work because the moment you find it, it's one of the properties like at V0 minus, you can immediately just say all this stuff. And you can use that value for the next states of the circuit. But for resistor, you're gonna have to make sure that again, this is I'll write it for both. So for resistor, what the V? RV0 minus will not be equal to RV as 0 plus, nor will it be equal at all. RV being the resistance voltage 0. That means I have to
Yeah.
check at every state its values. And the same goes for its current. Oh, that's saying. Just means I'm gonna be doing more work. Anywho, so for
Is the capacitor open or closed there? Or
I
what's
was
up
about to
with that?
change it just now.
Okay,
It's gonna be
okay.
open because it's
Yeah.
steady state. It's been connected to this voltage source, so it's been charged for quite some time. So
Yeah.
that means it's gonna be steady. So we're gonna erase it and make this open. And I'm gonna label this as BC 0 minus. And it doesn't matter what you do. This will be plus minus. All right. Let's see how we're gonna do this. So in fact, before anything, we're gonna simplify the circuit. Since we're looking for this current will be the same for this. So if I, since these aren't parallel, can I erase please? These aren't parallel. I'm gonna combine these, and the current will flow here, so I don't have to worry about that part. So I'm just gonna simplify the circuit down.
What are we looking for first?
Well, we're gonna look for two things actually. We're gonna look for this. Oh, they didn't change it. My bad. Not I0. This will be the I00 minus that we're looking for, because we're looking for the current of the resistor. All right, we're trying to write down the equation for the first order for the resistor.
Okay.
Does that make sense? Or
Yeah,
not?
we're finding the first order equation of the resistor for the,
Yes.
the current across the resistor, right?
Yes. Which
Okay.
which is why we're at all this. Right now we're at this
Yeah.
part. We're checking this.
Okay.
But instead we're I wrote L. My bad. This should be I. No. These are the currents. Here's the current. We're doing the bottom part because we're not asked for the voltage. So we're just doing this. We're checking every instance.
Okay.
So we're doing I00 minus, and we're looking for the voltage of the capacitor at 00 minus. Okay. So at this point, we just do circuit analysis. So you can do whichever way you want. You can do source transformation. You can do whatever you learned, current, voltage, division, and simplifying resistors down. For this, I could do current division. I could also do source transformation. But I'm just going to simplify. I'll simplify these two, combine them.
Mm-hmm.
If I do that.
Well, you could just do Ohm's law if you really wanted to, couldn't you?
Yeah. Oh wait, I should just do KVL. I just realized.
KVL?
Like to figure out
Yeah.
this current.
I mean, you could still simplify it first and then do KVL.
Yeah, you're right. So this would be 2. Wait, that's what I mean. There's multiple ways to solve this. This is 2.
Yeah. That's what I'm saying. You could just do Ohm's law if you added the three resistors together. Because they're on series, right?
Yeah, you're right.
Are they or no?
Hmm?
Are they in series technically if that's an open circuit in the middle?
Yes.
Okay. Sweet.
So Leon. Oh, all right. My bad.
Crazy.
This is 1. All right. And then we're still looking for this here. Is the current we're looking for? This is I00 minus. Hello. Trying to think here. Yeah, well, I'm just gonna do Ohm's law to solve for I0.
Yeah.
So for I0, you're gonna get 0 minus is just going to equal to 12 volts over 1 plus 2 plus 1 is equal to 3. We have that. Now for this voltage, we're gonna have to do KVL at the middle. Let me see. I ground this. I think I just do KVL in the middle. Yeah, wait, let's like so this if I do KVL real quick. All this. L1 and this L2. Oh yeah. That's the volts plus 1 times 1 plus VC. VC of 0 minus 0. We know L1 is equal to 3/8. What is that? Right? Oh, L1, I mean I1. Sorry. It's I1. And I1 is the same current both loops. Yeah, because it's IO. There's no current division, right? Nope. So we know that I1 is equal to 3A. That means you get VC. AC. So you get V C of 0 minus will equal to 12 volts minus 1 times 3A.
Why do we need VC?
This is the capacitor's voltage. We're gonna use it after.
Okay,
You'll
but
see
I thought
why.
we were just finding. Okay, I'll see. We'll see.
We need both. We need both.
Okay.
This would be 12 minus 3, so you get 9. I don't know if I think I do that.
Where did you find the I1? Do we find it before?
Yeah, I found it here. So this is I1 here. Ah, sorry. This is I1. It's the same current, right? So I would do just Ohm's law, which means I take this voltage, which is 12, and then since these are all in series, I just add them. So that's what I get here. 12 over 1 plus 3
Okay.
plus 1. Just Ohm's law.
So it's all around the big loop?
Yeah, because this is
So this is-
open. So this no current will flow down here. So it's just one big loop.
Okay.
So let me double check something real quick. If I do the other side, if I get
So
I get
L2 is
-1.
also 3A?
Which one?
Loop 2 is also 2A? 3A?
Yeah, I was about to just check something right now. Actually, it is because it's the same current.
Yeah, they should both
VC.
have some current in there.
VC plus 2 times.
Oh, you just did KVL for loop 1 then, right?
Yeah, I'm double checking something. Plus 1
Okay.
plus 3. 6. It works. Yeah. VC. I'm trying to double check my work. Equals to 6 plus 3, which equals 9. So it works. That means my VC is correct. So you could do KVL either loop. Just note that both of these loops is the same current. This one. So they're both
Okay.
3 in. Just know that. I'm double checking my work. Okay. The reason why you do this is because you're going to use in the next state of the circuit when it enters its transient state. Because now that you know this, you know that 0 minus is equal to 9 volts, right? That means it's also the same at VC of 0 plus, and it's also the same at V0. So now you have a variable that you can use freely, which is why you do that. It's important that you know this. Link. So now, number 2, we look at see how much space I have. I don't have much, so I'll make this smaller. But 2, look at state of circuit at t equals 0 plus. So at t equals 0 plus, the switch flips up. Yeah, meaning basically the whole right side is gone. Just the 2 resistors gone. So I'm gonna redraw everything, but with the 2 resistors on the right side. 3 plus minus 12 volts. I kind of forgot. What is it? It's 1 capacitor and then 3. See this 1. I'm gonna write the capacitor like this for now. Capacitor. This is 3. This is 1. Not 3. 2. My bad. It's 2. And then it's 2 here. 2. I'm gonna just do this so you know that the switch is here. So this is the switch. Thing flipped up. And then you're still looking for this current here. But now we're this instead of 0 minus, it's 0 plus. So that's that. And then we have, so the reason why we use that solve for that voltage for the capacitor is because now we can place it here, plus minus, and this would be the VC of 0 plus here, which we know to be 9 volts. So now we can use it in terms of our circuit analysis when we need to solve for I0 plus.
Okay.
For this case, I'll just do KVL. So this will be loop 1, this will be loop, make this neater. If you're confused why I can say this, it's because again the capacitor will hold its charge. It can't change instantaneously. So for this short period of time, it's gonna act like a 9 volt voltage source because it carries 9 volts from the previous state, which is why I can do this, by the way. Wink. Well, we're gonna do KVL here. We're gonna solve for the I0 plus, which is gonna equal to just the left loop current. Make a note of that here. I2. So KVL at loop 1. So you get minus 12 volts plus 1 times I1 plus 9 volts equals 0, and then KVL at loop 2, you get minus 9 volts plus 2 times
What are we solving for?
I2 for I0 plus, but through KVL.
We can do mesh analysis too.
Hey, that's what I'm doing right now.
Oh, okay. KVL different from mesh. What you talking about?
Huh? KVL is mesh.
No,
Adding voltage drops? How do you do that?
no. KVL and mesh are different, aren't they?
No. KCL and
Yeah.
node or what are you thinking about?
Okay, that's a separate
What is a
argument.
mesh?
Keep going.
Oh.
Mesh is when
The
you
loop,
include
no?
like the I1 minus I2 in the loop.
Yeah, there's
Because you have so
no,
like
no,
for
no.
loop 1, yeah.
Wait, this actually does it? Mesh is loop analysis.
If it was resistor, then yes.
I'm gonna let Patrick
Okay. The methods
with
are
it.
different. That's what I thought.
Ah.
You just do them differently. I don't know. That's how I have it in my head. Just keep working. It's fine.
Wait. Canelo, leave me alone. Get your squeaky toy out of here. Plus 2 by 2 equal to 0. So you get minus 9 volts. Just do this. 4 I2 is equal to 9 volts. Oh, bruh. I just realized. Yeah. Put it that way. I2 is equal to 9 over 4 amps, which is equal to I0, 0 plus. I mean, I guess over here, if you want to solve for it, this would be 9, 10, 11, minus 3. So I1 will equal to 3 volts over 1. It's 3A. So this is what we wanted. So I got that. So now we need to do one more thing. Yeah, but we need one more thing. We need to solve for tau. Let me make it smaller. So tau we get for the transient state. So it's going to be the same circuit, but goodness. Oh. There you go. Okay. I solve for tau. Solve for tau at transient state. That means when the circuit is fluctuating. So when the source is applied or when the switch is flipped, which is at T0 plus. So, and also, I'll just redraw it. Plus minus 12 volts. 1, this is the capacitor here. This is 2.
Because we have to find resistance, right?
Yes, that's what we're gonna do. So that's I'm keeping as a capacitor, just so people can see. Move this a bit down. So for tau, it changes depending on what type of circuit you have. We have a RC circuit here. So our tau is just going to equal to R times C.
We find tau when it's like 0 plus, right? Like just when the circuit is open at that moment, basically.
Yeah, well, basically, yeah, when it's changing.
That's
because
more like the thing, yeah.
yeah,
Okay.
this will be R dividend from C. The R dividend we're looking for is here. That also includes this resistor. This, and then we're going to kill off this. So this is killed off. This is opened. Oh, I don't want to restart. So this is going to be opened. This is also going to be opened. It's like you're summing arc dividend for Northern and Devon equivalents. So this is also, oh no, shorted. My bad. Yes, this is shorted. This is be shorted. That's shorted.
Sure, that's voltage should be open,
It's
right?
a voltage source. No, right? No, because for a capacitor, kind of no. Capacitor, when a steady state becomes open, but for a voltage source to kill it off, you have to short it. It's a bit weird.
That's weird. Just for
It is very
capacitor?
weird. Just for the thing. I don't know. The things I said before for the capacitor and inductor only apply to those. But for a voltage source, if you want to kill off a voltage source, you have to short it. And if you want to kill off a current source, you have to open it. So
So it's not like in Thevenin's equivalent
it,
circuits. It's different, right?
it isn't though. That's how you do it, right? I'm right, chat, right?
I think in
What's the question?
Thevenin's
Question?
Kill
we
off a voltage source in Thevenin and you short it, no?
voltage we open current where
Nice.
we short. But maybe
I
this is different.
thought that was the other way around.
It does?
Oh, I thought so. Maybe. I do check that. Check that.
What?
Devin.
Let's check.
What about them?
Oh my god. All right, hold on.
I was looking at them.
Start looking at work.
Okay.
Uh,
I'm pretty sure because
VTH
these
is
short of voltage
open
sources are no
circuit.
good. I know that. I don't
VTH
know.
is open circuit at terminals.
What about the last one? The last one we had it was the same thing. Let me see, right?
There's too many different
Yeah.
methods in my notebook now.
Just I could check here. Yeah, I'm right. You open circuit a current source, but you short a
circuit
voltage source.
Yeah.
That's what I was saying. Yeah, no, so yeah, I was right. So for current sources, you would okay. I'll do it right. I'll just show it here. If you have a current source,
Mm-hmm.
right? I'll do it this way. You have a current source 2A, right?
Oh, you have to open current source, right?
Yeah, exactly. Because then current won't
So
flow.
it doesn't flow. Yeah.
Yes,
oh my
yes,
god.
yes. You can think of it that way. And that's okay. Don't worry. But yeah, I'll short this voltage source and then I'll find Art Thevenin. So that means that this will be opened because of the capacitor's steady state. Maybe I should do it in a different color. So it's gonna be
Oh, now we're saying it's steady state.
yeah for tau because you want to kill it off.
Mm.
So that means your Art Thevenin will be the two resistors in series. Actually, all the resistors are in series. Yeah. So
The
you
way
get
this
Art.
was explained in class was a little
Yeah, how is it
different.
explained?
We basically said that at T0 plus, right? We have our entire circuit and we just kind of find the resistance equivalent of it however we can. So like for
Oh,
the
like the
circuit,
entire circuit.
yeah, we would have the entire circuit, right? So
Mm-hmm.
for this circuit, how would it be? So on the right side, there's two in series. I would combine them and then use like source transformation and then combine them in parallel, and that would be how I got the equivalent.
Oh.
That's how we did it in class for a few of them. I tried to do that for the homework too.
Can you write down what that is, like the way you're doing it? Because I have the answer, so you can see.
Do you have the correct answer?
Yeah, this comes with an answer.
Oh, really? Okay. What'd you get then for that one? Is
wait.
it
I think
so
you're right.
five?
Yeah.
You got 5?
Yeah, but then where's the 4 coming from?
Well, it's what is this? This is an LC circuit or what? RL circuit? RL?
No, it's RC.
RC? RC. My bad.
Yeah.
R times C. 15/4.
The balls did you get 15/4?
So you got 5/3. You got 5/3?
Yeah, I would get 5/3.
Okay. So okay, let me try this the way I was thinking about it. You go back down.
It was just parallel, right? So it'll be 4.
Yeah.
Maybe 1/4 plus just 1/1. 4/5. 4/5 times 1/3. Oh yeah, you get it. Oh, is that really how you do it?
I
Yeah,
guess.
because then it'll be flip. Huh? But I always been doing it the other way, and everything just works out.
I don't know. Wait, I got 4/15.
Yeah, but you flip it
Oh, really?
because it's tau divided by RC.
Oh, okay. Oh yeah, you're right. Well, yeah, that's how I was doing it for homework stuff and in class.
Oh.
It's
Oh
really
no, it
weird,
works.
Weird though. It's weird.
No way. Is it? No, it does not work because it's not parallel.
I got the same thing. What's wrong?
No, just
That
do
is
it.
actually a crazy pull. Like, where did RTH come from? We're just
Oh.
using principles.
Yeah, more
Like,
like
it'd be
just using
equivalent
principles right
type.
here. Yeah, because it's
Okay.
technically our equivalent for that. Yeah.
Wait,
Yeah.
you short a capacitor? Wait, let me see one second. One sec. Well, that makes sense though, because you are just finding with Thevenin ordinance. Yeah. Or Thevenin. Bruh. Who had it? Where is it? Let's see if I can find it. First order. Nope. Is it this one? I think it might be this one. Or I wish I had my notes. Oh, yeah, I found it. Wait. God damn. Okay. Okay, here we go. Okay. Is remove the inductor capacitor and find a Thevenin equivalent at the terminus which has been connected to. Would remove the capacitor. All right.
If you were to just leave the capacitor and treat the voltage source as a short circuit, you wouldn't get the same. You would get the same answer, wouldn't you?
Yeah, I'll give you the same answer. But now I don't know if I go back and do it that way, would it be the same?
What do you mean? It would be the same.
Oh, because I've done it all problems like this is my
We can't. I mean, if it's okay, transient state's just when the switch was flipped, so we can't say the capacitor is an open circuit because the capacitor is going to hold a charge of some type.
Hold just
Mm,
for a little bit, right?
mm-hmm.
Yeah.
But then it becomes a you would treat it as a voltage source, no? So you would short it. Ah, I see. And then
Yeah.
it would work. Yeah, if you do it that way,
Yeah.
because then you have a parallel branch. Maybe that is the way. I gotta go back.
Yeah, you can't. I mean, you can't just say it's an open circuit because it's a transient state. It's just when the switch is flipped.
Okay, I need to make note of that because there's 9 volts right now. And then yeah, so then this would die. Oh yeah, because that's how you find R Thevenin. You just do this. Yeah. So then you could do it. Okay, wait. My bad, Sylvia. We're gonna have to like.
Oh, it would make it parallel then.
Yeah. See what I mean?
Wow, that's actually better than my method. Yeah, you're right.
Wait, Sylvia. Do you get what happened? I kind of explained it a bit. Well, I was 80% correct, 20% wrong with the way I
Okay.
explained it. For we can't get rid of the capacity. We can't treat the capacitors like they're steady state because it's in a transient state, meaning that like it still has voltage. So this is the capacitor at the moment. This is the capacitor. So it's acting like a 9-volt source right now. The thing is, when you're looking for R Thevenin, remember when I said you have to kill off all the sources?
Okay.
To kill off this source, you would short it for any voltage source. You short it, right? Before I just told you to like open circuit the capacitor because it's in steady state, right? Which is wrong because it's not in steady state at the moment. It's in transient because you find tau at transient state. You know what I mean? So basically, take what I said before and kind of like alter it to like where like you would treat the capacitor with the charge it had initially, and it's a voltage source right now because it's in transient state.
Okay, but we're looking for resistance,
We're
right?
still looking for R Thevenin, yeah. But the way you look for R Thevenin with like Northern Thevenin is that you kill off all the sources, and then you're just left with resistors. To kill off the sources, you would short all the voltage sources. That's what I'm doing here. This is short. This is short. It's just a wire going through it. If it was a current source, you will open it. So if we had an inductor here, actually, if this was an inductor, I'll write a current source. I'll draw a current source and make it open. That's the only thing
Okay.
I'm telling you to change in your theory, or I guess your steps.
Okay, so what's the resistance?
So for this, it'll just be
No?
the two resistors in series. So we're gonna get 2 plus 2, and then this one is parallel. It's
Oh,
parallel
okay.
because
So
it's a wire.
you just combine all the resistance in the circuit, right?
Yeah. Yes.
Okay.
But the way I told you to kill off the sources was wrong. That's why I'm like trying to like
Okay.
clarify.
Oh, thank you.
Mm-hmm. Oh, that's how you do that. No, that is how you do it. 1/4. This one. 4/5 equals part Thevenin.
When we're finding our Thevenin, we always do it across the like. Where do we do it? Where are we finding our Thevenin?
Where they ask you to find the equation. We're asked to find
Okay.
I0 at that 2 resistors, so I start R Thevenin there.
Okay.
But if it was a capacitor, you would remove the capacitor, by the way. That's how I've been doing it.
You just make the capacitor to voltage source and makes it a short circuit, or what?
Or you're just gonna
Yes,
remove it. You put like
capacitor
R
right there.
Thevenin there. Like if I'm doing R Thevenin for like instead of the 2, if I had this in place, right? And I'm asked to find R Thevenin here. Because I'm asking to find VFT here.
Oh,
That means I'll
across
find
the
R
capacitor.
Thevenin here. Yeah. Because they're asking me to just find the voltage equation for a capacitor. So I'm trying to find tau here.
Okay.
So I just get rid of it. Because
Yeah.
it's not a resistor, right? You don't have to count it.
When you say get rid of it, you just make it an open circuit.
Yeah. Basically, yeah. You would have like, because like you won't count this. This I'm counting for because it's a resistor itself.
Well, finding R Thevenin against across the capacitor is its
It's
own
n-
like what?
It's not really a thing. You know what I mean?
No. Yeah.
Okay,
How
wait.
would
So
you do
this,
that? Whatever. Yeah.
I can go back maybe show you. So tau would equal to 4/5. 4/5 times the capacitance, which is 1/3. So you get 4/15. So now for the final part, I'll just do it here. Right out I of t. Your general equation is I of t will equal to I of infinity plus I of 0 plus. Make sure. Bruh. Where is it? Yeah, I of 0 plus minus I of infinity e minus t divided by tau. So we know everything. So we know that I of infinity is equal to. Oh, we didn't do I of infinity. God damn it. We still have to do that. Can't write that yet. Fudge. Okay. We still have to do I of infinity. My bad. Okay. Last thing is software. What do I do it? I'll do it here. Solve for state of circuit at t equals infinity. And now everything's back in steady state. So we'll just have the voltage source, 12 volts. Now this is open again. This is open. This would be 1 ohm. Then you have 2, 1. This is 2. This is 1. And then you're asked to find this. This would be I of infinity. Which again, actually, it would just be Ohm's law. We don't have to do much here. Yeah, this is Ohm's law. So I of infinity, which is equal to 12 volts divided by, 1 plus 2 plus 1, which is 4. Amps. Now we know everything we need. So now we know I of 0 minus, which is equal to 3a. I of 0 plus, which was equal to where is it?
Check your
Nine over
resistors.
four. Did I mess them up?
I think so on the far right. Is that a 1 or
I
a 2?
did. Thank you. This is 2. This is 2. Thanks. This will be 2.4. Okay. So we have I has 0 plus, which is equal 9 over 4. And then now we have I of infinity, which is equal to 2.40. And then we have tau. Tau is equal to, where's tau? 4/15. 4/15. And box it off. Okay, so now we can write the general equation. So I of t is equal to I of infinity plus I of 0 plus minus I of infinity e be e of negative t over tau. I think I got the right equation down.
Yes, it looks like, right?
Yeah.
For resistor.
Or for the general, yeah. Yeah. Okay. So we just plug in the values we have. So we have I of t will equal to 2.40 plus this will be 9 over 4 minus 2.40 e to the negative t. That was 4/15. So I'm just gonna write this as negative 15 over 4. There you go. Just simplify the middle. Good. I of t equals to 2.40 minus 0.15 e to the negative e over 4 e. And that should be your final answer.
All right, thank you. I'm gonna
right?
put it on my cheat
nice.
sheet.
It is right. There you
Thank you, Isaac. Thank
go.
you, guys.
Problem.
Have a good night
You
and
too. Sleep well.
rest of
Bye.
the spring break.
Bye.
Bye
Good luck on your
bye.
exam tomorrow. You got this.
Thank you. Good night.
Yeah. Yeah. Good night.
Good night. Let me upload a screenshot. Wait, any questions before I actually take the screenshot and upload it?
I have one question. I
Mm-hmm.
made like a small equation list cheat sheet, and when we have like source-free RC circuit, we're supposed to use V of t equals VO e to the negative t over tau. And then when do we use like that versus the step response equation?
This is general. You can use it for both, either
Oh,
source or not source. It's nice.
I guess yeah. When do we use one or the other then? I guess when do we use the source-free then? Just
I never use
well,
source free. I learned it through your slides. But if you
okay.
if you remember this equation, you can do it for both. Well, I
Okay.
don't know if I answered your question. You know what I mean? It works for both source free or
Yeah,
source.
I
It
get
doesn't
you.
matter. Okay.
I think source-free is because there's no infinities basically, because it's just
Yeah,
source-free.
exactly.
It's just gonna be what.
Because it dies out.
Yeah.
Yeah.
That
If
makes
you
sense.
after you shut this equal to 0, you get the equation. This will be 0. This will be 0.
Yeah.
So you just get this plus this, and that's what the source free is.
Mhm.
Hello.
Use my equation sheet if anybody wants it. It's a little bit blurry, but
Okay, I'll upload this right now. Hi,
I'm
Sylvia.
looking for. I'm looking for that upload picture.
Yeah, I was about to do
I
it.
thought it's. You will do it, or you did
Yeah,
it.
right now.
And I can't find it.
No, I'm doing it right now.
Okay.
the Discord chat. I'm deleting that. Yeah, I know. Pain.
This is here.
Huh?
There you go. Should be able to check.
Okay. Thank you. Again.
Wait. It's not. It didn't do it nicely. Okay, never mind. One sec. Let me get a screenshot. I don't know why it
Oh,
does that.
something happened.
Yeah. One second, I'll just get you a screenshot. Bro, OneNote sucks sometimes. There you go. That's better.
Perfect.
All right. Is that all?
Thank you.
Yeah, no problem. Good luck tomorrow. Have a good night now.
Bye.
Bye bye.
But
All right. Any other questions?
no, that was good. Not about this one, at least.
No. Okay. We're gonna do another first order. And this one we gotta be a bit fast about. There's one from your exams. This one's actually much easier too, because you'd have to do a resistor.
Oh wait.
It's nicer.
So
Ah.
what we just did was a LRC or RC circuit, right?
RC, but you aren't looking for a voltage or current through the capacitor. You're looking for the voltage current through a resistor, and that's what makes that problem so long. Yeah, you gotta make note
Okay.
that we did it through a resistor, which is why we have to check at all states. Normally, you don't have to do that. I mean, you'll
You
see
have to
here.
check it at all states for capacitor too, don't you? Well, I guess you don't, because some of the states you just know they're infinity, so it's gonna be like 0 or something.
You don't have to check it for 0 plus. Because-
Yeah, okay. You need the R7 though, which is like around.
Yes, you do need that. Well, I guess yeah, you'll write it again at 0 plus, but you won't solve for voltage there at 0 plus.
Yeah, makes sense.
Okay, we'll do this one.
Yeah, first order versus second order. I don't
Wait.
know what any of that means.
First order means it's a one current or one storage device. So it's you're dealing with one capacitor at a time or one inductor. But you have resistors. So anytime it's a first order circuit, you're gonna have either one inductor or one capacitor. Never both.
One storage device.
One storage device. Okay.
And then if it's a second order, you're gonna have two at the same time, which is why it's called LRC. Because you're having an inductor and a capacitor in there.
Okay. We haven't even gone over LRC yet, I thought. Did we?
You have. That's the
No?
slides. Yeah.
Oh. Okay.
Don't worry, I'll go over with them. Also, I was gonna say, if Patrick can I don't know, is he still recording? Did he stop it when I finished the problem? Can we just do a new one for this one?
He's still going.
It's an hour and 2 minute recording so far.
Okay. Wait, what?
Hour and 2 minute recording.
Oh, it's an hour and 2 minutes right now.
Okay, I mean it's whatever. Like whatever suits him, I guess.
Keep her going.
I'm gonna keep the whole thing if anyone wants to cut it up afterwards.
Okay, thank you, Patrick.
Mwah.
He said thank you. Wait, you have headphones on. What am I talking about? Or whatever.
All right. So here, this is what I was talking about. So you have IL 0 minus equals to IL 0 plus, which will equal to IL 0. So this we can use here because we're asked to find the current through the inductor. That makes life much easier. All right, we're asked to find, yeah, okay. So we're gonna do the same thing we've been doing. So look at, let me full screen this. Look at state of circuit at t equals 0 minus. So the switch flips up at t equals 0 minus. So it's gonna be flipped down. I'm gonna get this. That's fine. I don't know if you're gonna get a resistor problem. I'm not sure. Has she ever taught you guys to do with a resistor? Or even in the homeworks?
I still don't know the difference between this and what we just did.
Oh, okay. You're not. I'll show it. It's
Like, isn't it the same thing because we only had one device in it? Technically, with the
okay,
last
it's the same format of the problem. It's just like what you're asked for is different to find.
Like,
What you're asked to find is different because you can't use this. This here I can use now. Now you see. You know, I'll just show the work.
Yeah.
The work will make things easier. Okay,
Okay.
so this, I draw this, and then 6A. And then the inductor has been charged by the current source, so it's in steady state. So we're going to treat it as an open circuit. I mean, short. My bad. Let's do. Trying to find a way to make this the inductor. So we're asked to find. This will be the IL minus. Okay, Pat. What do I do? You guys should be able to solve this. Is this thing on? All right.
You're good. I was just writing stuff. What was it? Just to solve for what?
How would I solve for I L 0 minus?
0 minus. Zero minus. So before it's okay. So that's short circuit. And the weird little line there. Fun. The current.
Mm-hmm. You have to solve for I
Plus
L
1
0
plus 6.
minus because you're trying to write this equation for it. So I L of t is equal to
Yeah.
I have infinity plus I L 0 minus plus, oh, my bad, minus I L infinity e to the negative t over tau. That's what you're trying to write. So you need to know I L 0 minus.
Mhm.
How would you solve for it? Don't overthink it.
I'm
Would
overthinking
you
it.
just like, since it takes the path of least resistance, would it just be
Mhm.
6 times?
Is there a ground anywhere, or is this?
No,
Oh, okay.
that's what she said. It would be it'll take the path of least resistance. So basically this will get ignored because it's shorted. So this is gone,
Sure. Yeah. That's doesn't matter.
right? So this is gone. Then now what?
Well, it splits off at the 10 or the 10 resistor, doesn't it?
Mm-hmm. No,
Wait.
It
no, no,
chooses
no.
No, there's a short there. So wouldn't it just be 6 amps? Like, shouldn't you right?
6.
Yeah, it would be just 6.
Oh.
Sorry. Yeah, that's what you were saying. I
Yeah.
also I was looking at the 5 and the 10. I was like, wait.
Yeah.
But yeah,
That would throw me off. It's parallel. So.
it is a 6. Good job.
Really? Is it really? I guess I don't know. It's just throwing me off for some reason. Path least
Wait,
resistance.
one sec, chat. No, it's
It's-
not 6.
I was gonna say because it splits. It's a node there. Shouldn't it split? I don't know.
And déjalo. Wait, what's V equals 6 times 10, 60, 60 divided by 10? It is 6. No, I'm overthinking it. Wait, because you do current division. This is R equals 0. It is 6, yeah.
It's like
And then
putting
you're
a
gonna
wire
do
around the 10 ohm resistor. You're just skipping it completely. It's quite literally a short circuit.
R equals 0. It'll be 0,
Okay.
0 plus 10. Wait a minute. Why does the current division formula not work? Oh, because it's 10. My goofball. It is 6, my bad. I
Nice.
was trying to prove it in my head. So I can't see things if I don't prove it. So it's gonna be 10, 0 plus 10 times 6a, which gives you 6. My bad. Sorry about that. Hello? What the heck? And then, because you know that, now you're gonna have IL0 minus equals to IL0 plus, which equals to IL0, which equals to 6a. Now you know that, so you don't have to check for 0 plus. That's like the difference of this problem. I don't have to check what it is at 0 plus, because I already know what it is. With resistor, you do, because you don't know if it's gonna fluctuate.
At 0 plus, what? Whoa, why do we know it's 0 plus?
Because it's an inductor, so the current won't like instantaneously change. It's gonna stay at 6a.
Oh,
Up and
0 plus. Never mind. I was thinking 0 infinity. Yeah. It
hey, that's the
lingers.
difference. Yeah,
It
it
lingers.
lingers. For a resistor, no. Like for a resistor, I had to check.
Yeah, instant for the resistor.
Do you get it though? No. Like, what's the difference now?
Yeah. I was still writing it
Okay.
down. I'm like on the short circuit part still.
So now we look at state circuit at t equals infinity. So at t equals infinity, this switch has been flipped up. So legit, all you're left with is just this. So you have this. You have the inductor once again shorted. have 10. I think this was 6. Yeah. 6a, 10. And then you're asked to find this here. This will be IL of infinity. Okay. So now what? Oh, no, this is broken. My bad. This is, yes, this is broken. The switch is here. All right. So what's IO of infinity?
6 amps? No, it's broken. 0.
Yeah, it's 0.
Okay.
So IO of infinity is 0. Okay. Now we solve for tau.
Wait, sorry, why is it broken?
This is a switch. It got flipped. This is a switch.
Oh, okay, got it.
And we're looking at infinity now.
T infinity. Wait, T0 plus. Why would that be 6 amps? Oh, because it lingers. Never mind.
It's all good.
Even if it's broken, it still lingers for just like a second or milliseconds or whatever.
Mhm. So now we go ahead and look for tau. So this would be broken. I'm just going to write it like that. This is the inductor. I think the inductor is 1.5. This is 1.5 henries. This is the resistor. It's A. And this is 10. So we look for R Thevenin here. This is a problem. Oh no, wait, one sec. Chat, wait, I forgot. I forgot this resistor. It's not 0. This is not connected to this is still here. Oh, aye. My bad. This is 5 ohms. It's not 0.
It's not 0 then.
I
Ooh.
forgot. My bad, my bad. I didn't see the 5 resistor. So what is it then? I'm awful. You gotta catch me.
Hmm.
I'm just drinking my coffee.
6 amps?
Mm-mm.
No.
Mm. Unless you
It's
did the
still
math that fast in your head.
no. I mean, it's still path of least resistance, isn't it? It's going through the 5 ohm, but it hasn't gone through it yet at the top side. I thought
But it will go through the 5 ohm.
it will eventually.
Yeah, but yeah. So
It's a race, bro.
No, it's
Eventually,
not. Are you
eventually.
sure
what are the
it's
10
not
and the 5 ohms related? How are they related? They're what?
parallel?
Yeah. So what do you do?
I don't know. Some magic.
Current division.
Current division.
It's the
Well, not
resistor
current
you don't
division.
want, right?
No, we're looking for the
It's
current
the
through the
branch you
5 ohm
don't want.
resistor. Wow.
Yes, the one you
Good
don't
read.
want.
So the
current through
10.
5 ohm resistor.
Correct.
And then over 15. I got
Yeah.
4.
Yeah, there you go. That's what I was like. I thought you did the math that fast.
No, I'm just not that skilled. Sorry.
Oh, trust Leon. So if it's wrong, it's Leon's fault. Sorry. All right, my bad.
Womp womp.
It's 4A. Okay, so that means that this is still here. So that makes sense because I was pondering like, how the fuck do you solve this? Okay, so what is R7?
Yes.
Anybody can answer. It doesn't have to be a little electrician.
I'm 20.
How do you do that again? We get rid
You-
of the 6 amps, right?
You just how you saw with Thevenin, you would do what to it? If you're trying to find art Thevenin for a Thevenin circuit or Thevenin equivalents. What do you do to current sources to kill it?
Current open. Open.
Oh, yeah, so you open it. So this is open now.
Shut up, Matthew. Yeah.
And then what is art Thevenin?
Yes. Oh, parallel. Series 5 plus 10, 15? Or no? Is the switch
Oh,
there? Switch is open.
are they in series?
Yeah, I thought they were series till 15, right?
Yeah, it would be serious. So 15.
Woohoo. See you around the day.
Everyone agree? Okay, open. So it's 15 ohms. So that means the tau would be, for our case, we have a LR circuit, so tau is L over R. So we're gonna have, I think tau is, yeah, so L is 1.5, R is 15, that'll be your tau. Tau is 0.1. 0.1. So now we got everything. So we know that I of 0 minus was equal to, what was it again? 6. I L of infinity is equal to 4. And tau is equal to 0.1. So when we write the equation, I L of t is going to equal to I L of infinity plus I L of 0 minus minus, my bad, 0 minus minus I L of infinity, watch, infinity e to the minus t over tau. So we get I of t is going to equal to 4a plus 6a minus 4a over e to the 1 over 0.1 is 10, so I'm going to write negative 10t. So your final answer would just be I of t equals to 4a plus 2ae to the minus 10t. There you go. Any questions?
Here's the main question. What's the difference between this one and the last one we just did?
Yeah. So look. So you see how I didn't do 0 plus anywhere besides I guess tau, but I didn't analyze IL 0 plus because I already
Well,
know
this
because of
is just because we're going across an inductor, though, right?
yeah, exactly. That's what I'm trying to
Okay,
say. Like
so
Hmm.
what? This is first order. The last one was also technically first order, right?
Yeah.
So first order is the same thing as just doing like an RL circuit. There's not really a big difference.
First order is an RL circuit.
Yes,
That's
first. Okay.
first order
Okay.
is an RL circuit or an RC circuit. Either or. Those are first
Okay.
orders.
And
It's just
second
like
order is RLC.
RLC, yeah. But then you have
Oh,
series and parallel systems for those.
That would be like
for
two
RLC.
elements.
That would be
Then
2
once you
elements.
add another
Correct.
one,
Yeah, yeah. Once you add another one, you get
then it
second order.
becomes a second. Gotcha.
Yeah, if you add another one, it becomes third order.
Okay. Okay. So this is very simple for first. First order simple. Second order not bad. Or
Second order is
it is bad.
bonkers.
It's bonkers. It's very bad. Yeah.
All right, but I just want to make sure you guys get this so that
Yeah.
because you need to understand first order because I won't go back.
I love first order.
The only thing you can be able to love right now, bro.
Yeah, pretty much. I'll take it where I can get it. Can you zoom in real quick? I didn't get to write everything. Or at the bottom.
Okay, yeah, sorry.
Thank you.
Mm-hmm. Mm. For those who came in late, I'm uploading all the screenshot of the problems in the chat, and the gentleman Patrick is recording all this, so he'll be up. Hopefully, he'll be able to upload it by tonight. If not, maybe tomorrow.
Oh, yeah, thank you.
Okay.
Are we gonna use step functions also?
Oh, I wish you were here last time. Fuck.
I tried to rush the recording from last one, but it cut off at the end.
I didn't go over step functions. I thought I explained it like really fast what they are.
You probably did, but like I'm saying, the recording actually just cut off while you guys were about to do another question, so I didn't get to see all of it.
I need to look at it. I can go right now, fast.
Okay.
It's
Is
not
Is it
super
Joey's one?
complicated. It is-
Yeah, I had like
yeah.
2 questions from the homework that were like they had no switch or anything. It just said do step function, step response.
It's okay. I'll show you right now, really fast.
Okay.
It's not that complicated. But then we have to do second order, at least a little bit.
Second order, we don't have till not next week, but the week after that. The first exam only covers first order stuff.
Oh, I wish. Okay, thanks. I didn't know that.
Yeah.
Thanks.
That's what
Okay.
the email said, right? The one I sent in the group chat as well.
I kind
It
of forgot it.
says it's fine. I just copied and pasted what she said. Where is it? Yeah. So part 1, Thursday, April 3rd, 3 problems: op amp, RC response, and RL response. And then for
Mm.
part 2, Thursday, April
Mhm.
10th, 2 problems:
Okay.
RLC and RL or RLC series and RLC parallel. So that's second order for the second one, which is April 10th.
Okay. Good to know.
Yeah.
Good to know.
So we have time. We don't have to do all the RLC stuff today.
At least a little bit. Explain you
Yeah,
guys
let's
get a
do it.
general gist.
I
But
would love
okay,
to learn more.
step functions. They're not super complicated. It's just a way we're able to graphically represent the state of a switch or what happens at a switch. So a step function essentially is like kind of a graph of a switch. In this case, my switch, I'm supposed to do this. My switch here, I'm flipping it at t equals 0. And let's say the u or the y-axis can be either voltage or current. It's just a representation of what's happening at the switch. For example, let's say the u here is 1 volt. What this is saying is that before my switch is flipped, nothing's happening. After my switch is flipped, a volt source is applied or some voltage is applied. You know what I mean? That's what that gives us this function, this ramp. It's because it's a switch being flipped on and off.
So it's quite
That's
literally
what a step
just
function
switch
is.
jumping from one thing to
Yeah.
another.
Yes.
Okay.
So for example, if I'm given something like this, I say for u of t, right? That
Mhm.
means that I have two things. So the domain of a step function, the important parts at least, is t less than 0 and t greater than 0, right? So that's what you're worried about. So for this graph, the step function will look something like this. So at 0, nothing's happening, right? Because the switch has been flipped. And at 0, it's flipped, and then it jumps to the value that it's in front of the step function, which is this amplitude, which is 4. It's going to be 4a because it's a current source. That's what the step function says. It just gives a visual representation of some source that is flipped on and off via switching.
Okay, that makes sense.
Yeah. But the thing is, the step function can be changed. It can be altered through graphical identities, I guess. I don't recall. For example, here, you see how this is moved now? This is moved by some t0. If I subtract t0 from the switch, it moves the time of it. For example, if I subtract 2 seconds from it, it's going to move to the right 2 seconds, and it's going to flip at 2 seconds.
Okay.
You know what I mean?
So yeah, I got the basic idea of the step function. When a switch is open or closed, the voltage source. If you have like a voltage source that relies on the step function, that means
Yeah.
that if the switch is open, you're gonna have a voltage source, or maybe not. I don't know. It's one of those two. I have it written down somewhere. But for the question that I had on the homework, there's no switch, and I'm given a step function. Here, I'll just stream it.
Let me see.
Am I still streaming? Oh. Well, here. There you go. There's no switch, but you're given step response. Yeah.
Yeah. So look, your voltage source it's a step response, meaning like it's gonna. Okay, here. What is it? Vs equals what? 18.
18. Yeah.
The reason it's because they don't want to tell you like before it's this, after it's this. They just give it to you in terms of a graph. So this is minus Vs, right? Vs is 18U.
Yeah.
So that means that you're gonna have this. Okay, it's gonna be sloppy because I'm running fast.
That's fine.
It's like this, right? This is gonna be 18 volts. It's 18? Yeah, 18, yeah. 18U2.
Yeah. And for anyone
Means,
wondering, this
for
is number
example,
6 on homework 2.
remember when we were solving for a t less than 0? The thing is, your circuit is going to look different at t less than 0 and t greater than 0 because your Vs is going to change. So when I draw the state of the circuit at t equal to 0 minus, my voltage source is 0. So I just have this. This is equals V equals 0 here. The voltage source will be here, but it's 0 volts. So it's going to be that, and then you would draw the rest. Oh, my bad. It's going to look like that. And then your inductor, my bad. But the voltage source would be here. Your Vs is here, but it's 0 at the moment.
It's as good as a short.
Yeah, it's like a short because it's a step function. Anything before 0 is a 0. When it's flipped at t0 plus, now it changes. Now you actually have a source now, and it's going to be the amplitude of the unit step, which is 18. So it's going to be 18 volts.
Oh wait, so are you just saying the source is just turning on and off, or what?
Yeah, exactly. Yeah.
Oh, okay.
That's all that does. They don't want to tell you what it is as 0 minus and 0 plus. They give you a thing that does both.
Okay, so how would we find an equation for that then? Can we still use the the L equation, whatever it was called? I forgot.
Yeah,
Unit
that's a
okay.
separate response. You do the general. You do what I did. T0 minus,
Yeah, the general
T0
step
plus.
response. But
Yeah.
so basically our source is just like turning on and off. That's it.
Yeah.
It's becoming a short circuit.
Yeah.
Okay, that's fine. That makes sense. Thank you.
It could also change too. It could be like just really quick. It could flip. So if they do like U minus T, that means that it's like been reversed on the y-axis. So it's gonna look like this instead. Just FYI. So it does happen. But that's all I got for unit step. There's not much to it.
No, that makes total sense. I was just didn't understand how it worked without a switch in the circuit because I was like, but it's just based off the time. That's really it.
Yeah,
It
it's based
changes
off
based
that
off
source.
of when something happens. Yes.
Yeah. Okay. Anything else before I move on to second order? Because no. All right. I think I uploaded both screenshots. Let me see. This is a second. That's a second. Yeah. Okay. All right. So general basis. Okay. Actually, let me start with this. I learned to do this differently. I was taught with the equations, like you guys are, with the overdamped, critically damped, and underdamped, but I did it the hard way. I didn't solve using those. Those are the shortcut methods, quote unquote. I solved using the characteristic equation. I wrote down full differentials for all my circuits just for practice. So I never memorized the equations. I just always did it by hand and like through writing down equations, KVL, and KCLs. So I didn't have to memorize the formulas. I could just do it like that, and I used differential equations to solve my problems, which I'll show you how to do that too. But either way, it doesn't matter. You can solve using the shortcuts you've been taught, or you can solve the way I did it. I'll teach both.
You're insane,
Yeah.
bro.
But here we go. So, like I said before, a second order circuit basically is a circuit with two storage holding devices, meaning you have two capacitors, one capacitor, one inductor, or two inductors. That's what gives it the second order property. That's all that. This is all what this slide is saying. But also, maybe one more thing. When you're taught this, you're taught there's two different configurations. You have the series RLC, which is where the capacitor and the inductor and the resistor are in series, or you have the parallel RLC, where everything's in parallel. That would change the way you use your equations. That you're gonna have a different set of equations for this, which is why I'm gonna do this tomorrow. We're gonna do only series today, but it's still like a lot. Like it's only a little bit changes for parallel. Okay, so the conditions are the same. So what you learn for first order, those capacitors and those inductors, the same conditions apply. The voltage through a capacitor won't change instantaneously, and the current through an inductor either won't change instantaneously. And again, you already seen this. These are the steady states I've been talking about a lot. So you have them here. And then you have these are the general equations. So if you're going to do characteristic method, or you're going to solve using time domain, which means just writing down all the differentials, you're going to need to know these equations. These are very important because you're going to write them using this. Because when you do nodal or when you do mesh analysis, you're writing down voltages, so you're going to be using this equation a lot and these equations a lot. So they're just good to keep in mind. All right, I think she does this here. She solves it using this. But we're going to do this problem. Yeah, we're going to do this one. Also, this stands for a single pole, single throw, if someone was curious. Let's see, what are we asked to find? So I'm asked to find V of 0 plus and I of 0 plus. So we're going to do steady state. So at, 0 plus. What is 0 plus? 0 plus, the switch is flipped down. So that means it's in steady state. No, I would just have to do. Thinking. Yeah, it'll reach steady state. Yeah, because I'll look for it. Okay, I got it. All right, for part A, we know that again for the steady state conditions, we know that VL. Oops, sorry. VL of let me full screen. VL 0 plus will be equal to V. Not VL, VC. VC of 0 plus is going to equal to VC of 0 minus, which is equal to VC of 0. That's because of the instantaneous property. And then you know that IL of 0 plus will equal to IL 0 minus, which will also equal to IL. Nothing new yet, which means I only really have to solve for IL 0 minus and VC 0 minus. So I'm going to take the state of the circuit before the switch is flipped up. Because yeah, the switch is being flipped up at t equals 0. So I'm going to redraw real quick. Let me zoom out so you can see the problem. So this will be too big. So volts. You have the resistor. Then you have your inductor. Oh, it's in steady state, so you get shorted. This will be the inductor here. And then the switch is flipped down, has not been flipped up. And then you have your open source capacitor. So I'll do in blue. Ah. And then let's follow convention. So the current's gonna go like this. So this one. IL of 0 minus. So now this is 2. Okay. So now we just do any circuit analysis to solve for this. What would IL of 0 minus be? I think that's easy to do first. What would you do?
And we'll just do Ohm's law.
Yep. You do Ohm's
Okay.
law. So you get,
Which circuit is this? This is when
yeah, I can show you. This is
T
the.
equals. Yeah. No, I mean
So-
like the one you redrew. Is that T infinity, T
Oh,
negative, or
this is
yeah.
yeah, my bad. This is at t equals 0 minus.
There we go. Thank you.
So this is going to be IL 0 minus will equal to 12 volts over 4 plus 2. You have that. Wait a minute. Okay. Because the current won't flow here. The current's not going to flow here. So this is just the same current. So now what is VC? How would you solve for that? Any takers?
I could say it, but I'm waiting on someone else.
Me. Tough crowd. All right, fine. So VC would be this. This is the same because they're parallel. So you could do voltage division for this. So to get VC of 0 minus, you would do 2 or 2 plus 4 minus the 12 volts, which would just be 6 times 12, which gives you 4. Cool. So now you know that. So what does that give you? That means that you now know IL 0 minus, which we said before was IL 0 plus. My bad. IL of 0 plus, which equals to IL of 0, which will also equal to 2A. And then VC of 0 minus equals to VC of 0 plus, which equals to VC of 0, which is now 4A. So now we have those values. We're also asked to find di dt 0 and dt dt 0. So I'm going to draw a different circuit. And I'll have to
4
do it
volts.
at...
4 volts. 4 volts. Not amps. 4 volts. Volts.
Oh, thank you.
Yeah.
Gotta make sure. I think she had to draw the... Yeah, okay. So for... We'll do it over here. For B, D, one second. I need to pull something out real quick. So, yeah, you could do it that way. Let's you do it that way too. She does. Okay, cool. All right. So you have these equations you could use. So for an inductor, you had the voltage. Oh, the voltage of an inductor is equal to L di dt, and you have the current. I just did here. You had the current capacitor is going to equal to C dV over dt. And the reason why we use this is because to find di at 0 plus, we'll just do this. So VL will equal to L di 0 plus or dt, and I of C will equal to C dB of 0 plus or dt. We know I of 0 plus. What's I 0 plus? B2. Make sure I'm doing this right. Hey? I messed up. Oh, my bad. Wait. If I do the 0 plus, that means this 0 plus applies here too. And then that means that this also 0 plus. Will be I of C 0 plus. BL 0 plus was equal to, where is it? Well, I'll just write it in terms of the I. So the I 0 plus dt is going to equal to 1 over L BL 0 plus. The voltage through the inductor at this state is 0 because it's shorted. See? It's always going to be shorted too. So that means that, wait, I'm going to write this down here.
What are we doing?
Kind of proving, like, we're just solving for this. This here.
Okay.
So I'm writing the differential in terms of the times. So like we know these
Okay.
equations. These are the equations you know. I just plug in 0 plus for this, and then 0 plus for this and this. Because these are, I guess normally you write them like this. You can write them as IFT, IFT. So basically plug in 0 plus for that t.
We need to find the value of di 0 plus over dt. That's the whole
Yeah.
goal we're doing right now.
Yes,
right?
that's legit just the whole goal. Yeah.
Okay, and you're just solving for that as a
Yeah. As
something?
using
Okay.
the equations. Yeah.
Yeah, okay.
It's a bit weird, but I guess we're doing it. 1 over L. The voltage through the inductor at 0 plus will be 0 because the inductor is going to be shorted. Once again, yeah. I don't know why I don't know why she doesn't write it. She just writes it 0. Well, it's because the voltage through the inductor is shorted, so it's 0. So this would be di 0 plus dt equals to 1 over L 0, which equals 0.
It's shorter for 0 plus?
Mm-hmm.
It's mm, why is it shorter? I thought that
Wait,
only happened when we were like at infinity or something.
wait. Did I miss something?
I thought 0 plus was before.
Mm.
The switch is flipped up. Wait, this would be. So now, wait, what did I say? It's 2.
Where's the confusion?
2a plus gi. I mean, the derivative of that is 0. Wait. What did you do for dbc? Okay. Fair enough. So where did she get the 0 from? the switch is flipped, and then you have. If I do KVL, hmm, TB, and then this is equal to ICF plus. Yeah. Well, if I derive, bing. Wait, what is the current capacitor 0 plus? Current capacitor 0 plus is going to be equal to this. Yeah, which she does. Yeah. Wait, how did she get 0 for VL? Why is VL 0? It's going to be the current of the inductor when the switch is flipped. But how is it 0? Hmm. Oh, I don't get the VL part. Bro. I'm stuck actually. I do the node analysis. This would be the IDT 0. Voltage of the inductor at 0 plus. Is it not just I did voltage division? Oh wait. I mean, I can only think of it because it's 0 here, but that doesn't make sense. Odd. I actually don't get why it's 0. See my notes. I wonder if I have a proof here, real quick. LDI. Or wait, that's my old notes. EBC, not the IDT. Odd. I don't know what that bit. Oh wait. Okay. So for DID 0, apply QPL. QPL that way. Am I missing it? So I'll get this will be I of 0. Not just 0. This would be 4 I of 0 plus VL, which is equal to L di of 0 plus VT plus VC. Yeah, plus VC of 0 plus. It's not 0. What the fuck is it 0? Because then this is 4 volts. Yeah, we know this is 4 volts. We know this would just be 4 I 0 or minus 12. So we're going to get minus 12 plus 4 I of 0 plus L di of 0 plus dt plus 4 volts equals 0. So you get that L di of 0 plus dt is minus a. So this would be plus 4 I of 0 plus is equal to minus a, which is equal to 8 volts. Then you divide everything by L. And then I need to know how would I get I of 0 plus? Wait, do I know I of 0 plus? So we got I of 0. Yeah, it equals to I of 0 minus. Yes, this would be 2a. So yeah, this is 2a. Because I know that. So I get L, and I get, right, I get di 0 plus dt plus 4 over L, right, equals to 8 over, you go to 2, so you get di. What's L? L is 0.25. 4 divided by 0.25 is 16. It's 2a. 8 divided by 32. Oh, why doesn't she show that? She just wait. Okay, it is 0. What the fudge? She doesn't put in her slides. Okay. Oh my god, I'm sorry. All right. The way we do this to prove the I0 plus, I kind of already. Well, I'm showing the method how you would solve RLC. Is writing the characteristic equation down. So to here, I don't want to erase my work, but I'll redo it. Okay. How do I do this? Okay. So for now, I'm just trying to solve for this. I know this. VL of 0 plus. That's what I know, which is equal to LDI of 0 plus over dt. That means I'm going to draw the state of the circuit at 0 plus. So I'm going to redraw the circuit doing this. This is plus minus 12 volts. This is 4 ohms. I don't know why she doesn't write it in their slides. This is 0.25. 0.25 Henry. The switch is flipped up, so it doesn't go that way, and then you have this. Brother, I'm busy. Oh god. It's like okay. So then you have this capacitor, which we're going to call VC of 0 plus. Yes. Okay. So if I write KVL around this loop, just do that. I'm gonna get minus 12 volts plus this KVL loop or current I'm looking for is I0 plus. So right there. So this is I0 plus. And it's produced from the inductor. Because the inductor is the thing that produces the current. So really, this is just IL of 0 plus. So I'm gonna get plus 4 times IL of 0 plus the voltage through the inductor, which I'm just going to write as VL, and then plus VC of 0 plus. Sorry, I should write this as VL of 0 plus VC of 0 plus equal to 0. Now I'm gonna write the equation or the KVL equation in terms of differentials. So I'm gonna write minus 12 volts plus 4. This stays the same because it's a resistor. This is gonna be plus L di of 0 plus over dt. This we know. This we know from previously. This VC 0 plus. We got 4 volts. So it's gonna be plus 4 volts equal to 0. Okay. Now we're gonna solve for di of 0. Di of 0 plus dt. This is what we're trying to solve for. So we know that IL 0, we already know I have IL 0 plus from before. It's going to equal to IL 0 minus, which is 2A. So we're going to have minus 12 volts plus 4 times 2A plus L. L is just the inductance. So we're going to have 0.25 henries times di of 0 plus over dt plus 4 volts equal to 0. So now we just solve for di of 0 plus. So we're going to have di of 0 plus over dt equal to, so minus 4 times, 4 minus 2 times A minus 4 volts, all divided by 0.25. And that should give you 0. That's why it's 0. Again, I don't know why she didn't write there in her slides. I might have gone too fast. So if I need to repeat myself, let me know. Yeah, it's 0.
What happened with the thing equaling 0 again?
Which part?
We said that
This?
it was equal to 0 or something? No, di 0 plus over dt equals 1 over L, which is equal to 0.
Yeah, but the thing is, I didn't know how to prove that. She just wrote it down. And I was like, that's what I was stuck on. I
Yeah.
was like, I proved it just now using the
Oh,
KVL
does it
around the
matter?
loop.
Does it matter? Why does it matter right now? That's what I'm asking.
It matters because this is how you solve the problems, by doing what I just did. And because you're gonna be asked if you're for these type of problems, you're gonna be asked to find what you did before first order, which is like the IL 0 minus 0 plus and the VC of 0 minus 0 plus. But right after that, you're also gonna be asked to solve for the differential ones, which is the DV 0 plus and DL 0 plus, those stuff. So you're basically gonna have to find the differential part too, on top of what you already know how to do, and that's how you do it.
Hmm.
It's weird, but basically what I did. Okay, this is what I did. So I know these are the variables I solved for. We both solved for them together.
Yeah, we
They're
got
not
the.
that bad.
Yeah.
Okay, and then the question asked me to solve for this, and it's
Yep.
important because you need all these for second order. So you need all these variables. So we solved for the first one. Now we're solving for the second one. For the
Okay.
second one, the way I do is you're gonna have to use some sort of KVL or KCL analysis. If you do KVL, you already know that you're relating all the elements in terms of voltages, right?
Yeah.
The voltage equation for an inductor, which is this I0 plus, is this. So if I relate it using the voltages, I can write down this equation and then solve for this di of 0 plus that I'm talking about, which is what I did. Oh, sorry. Let me
You
know.
just lost me. You went a little fast.
I lost you?
Yeah. Say
Okay,
again?
okay. So I do KVL. I do KVL analysis because the VL has LDIDT in it, right?
Yep.
It's the voltage of an inductor. So if I find a way to relate the voltage of an inductor with everything else, then I can plug this in and solve for it, right?
Oh, sure.
And the
Yeah.
only way to do that is to do KBL or loop analysis, right?
Don't you still have two unknowns then?
Say it again.
Well, do you still have two unknowns because you're including the inductor as well, or no?
No, the L is given to us. L is always given to us. It's here.
No, I mean like okay. So you have di 0 plus over dt, and you have dv over 0 plus over dt, right?
dV over
Well, what
0
else
plus.
is for
No,
current?
this,
Oh,
yeah,
okay.
exactly. So I
Yeah.
have to
So
use
you
nodal analysis for this. I'll use the
yeah.
other one
Okay.
to relate it.
Okay.
That's
So
what I
you're
did
just
though.
relating it using the KC or KVL? KVL. Yeah.
Yes, KBL.
Okay.
So I did the
And you
loop
can
of
just solve
0
for
plus. Yeah, and I can solve for it. And this
it.
is
Okay.
just we know already because it's just VC. Oh, I should write.
Yeah.
Sorry, this is the capacitor. My bad. Not it's not open. I just put it as capacitor. But we know it already. It's the same from before.
Yeah.
You know what I mean? It's weird. I might be doing a bad job at explaining this, but That's kind of how you do these type of problems. You relate it using a nodal analysis or a loop analysis or KVL.
Oh wait, go back. You drew another picture, didn't you, for the
Yeah.
circuit?
I did
Did you?
this.
Is
This is
the
jumbo.
I
This is
know on the
jumbo.
bottom though. Is there
One sec, I'll erase this
what
real
happened
quick.
to the 2 ohm resistor?
It's open. Switch is
No,
flipped.
the bottom left.
Switch is flipped. 0
Where's
plus.
the switch? I didn't write the switch down. That's why. Okay, that makes sense.
Well, a lot of people left. Isn't that good? I just hope I gotta explain it better here then.
Okay. How many people? Nah, not a lot of people. Still a lot of people here.
Really? Oh my
Yeah.
my overlay must be
1, 2, 3, 4. There's 8 people here.
Because we're not talking.
Yeah. There's
oh
7 people here.
damn. Never mind. My overlay lied to me.
Uh,
Okay. What else? What else? Alright,
Wait,
we
so
did
your
that.
circuit at t
Yeah.
equals 0 minus. There's a capacitor there?
They're mother. Alright, Leon. No, you wouldn't do that. I'm doing it for this one.
Yeah,
This one,
others.
yes. There you go. This is what I had before. No. You would do steady state for 0 minus. Sorry. Thank you for asking that. Okay, so we have that. That's why it's 0, just to get that, which proves that. Now for the IC, she finds it using.
I'm gonna mute it.
Actually, what does she even do? Does she even solve for it? I don't think she solves for it. VC, IC. Oh my god, bro. How does she solve for it? You would do nodal, but you don't have to because you know that it's equal to IC of 0 plus. Do we know IC of 0 plus? Oh, we do now. It's wait, do we? Oh, bruh, she proved it here. This is for this block. Anyway.
Your notes are funny like that.
Bro, why? I thought this was for this.
No.
Well, anywho, there's the proof. Is what I did. But I wrote
Yeah.
down the whole equations. What does she do? She says that dVc over dt is equal to 2 amps over 0.1. Wait. I just need to write it out so I can actually understand what's happening. So we need to find dV 0 plus dt. The
Can I see
equation
the
we're going to use.
KVL really quick again?
Sure. Yeah. There you go.
Ooh. Isn't that 4 times 2 plus 4? 4 times 2 plus 4, right?
4 times 2 what?
I'm making 0.
Yeah, isn't that 0?
Yeah. Exactly. It's 0.
Oh, that's the proof. Oh, okay, never
Yeah.
mind. I see it.
Now you're chilling.
I didn't get it, but now I do.
Why is this incredible?
Okay, so we know we can use this relation. So for I of C of t is equal to C dV t over dt. And then make sure, I think she used the same equation. Yes, okay. So that means that to get IC 0 plus, that will equal to C dV C of 0 plus over dt. And that means dV, right in purple, that means that dVc of 0 plus over dt will equal to 1 over c times I of c 0 plus. Okay, so now we have to see if we know the current through the capacitor, which we do. It's the same as IL. See? This current, the same as IL. So we do know it. So we can use the equation immediately. So we know that dVc of 0 plus over dt is going to equal 1 over c times IL of 0 plus. IL of 0 plus was just 2. So that means we get dVc 0 plus dt equals to 1. What was the capacitance? 0.1. Hello, there you go. 1 over 0.1. I forgot the ion. Times 2. And this should equal to 20, right? Pretty sure. Yeah, 20 volts. And I'm gonna move this over. I'm gonna move this over here. There you go. So this was solving for the di is 0 plus, and this solved for the dB. Make sure I got the same answer. Yeah, 20 volts. Oh, sorry. These are in terms of time too. So it's gonna be seconds. This would be amps over seconds, but we don't have that because it's 0. Okay, so we did that. That's part B. I think part C asks for infinity. So we're just looking at the state of the circuit at infinity. So I'm gonna erase this. I'm gonna call this. I'm gonna organize my work. B. Actually, wait. How do I organize this? Oh, whatever. Okay. So now we're gonna do C. So C solve for B of infinity and I of infinity. My guess is VL and VIC. Yeah. Oh no, VC. So VC of infinity, IL of infinity. Okay. So we just draw the same circuit again, but we're going to do steady states. So this plus minus 12 volts. My 4 ohm resistor. This will be shorted, so this will be the conductor here. The switch is flipped, so that 2 ohm resistor is no longer there. And now I just have this. I'll do this in a different color. I'll just have this. And then this will be the. And this will be the IL of infinity. So what would IL of infinity be here? That shouldn't be too bad.
Zero?
Yep. And then VC.
VC. 12 volts?
Yeah. Nice. And there you go. That's it.
How would it be negative 12 volts if the signs are flipped in any way?
No, the 4 ohm is dead. But yeah, it would be negative if the signs were flipped.
Okay.
But you wouldn't make your life complicated, so you just match it.
Oh, yeah. Well, you can just assume the signs, right, or no?
Yeah. You assume the signs, but like at the end of the day, like it will be parallel voltages. So you just make them the same.
Yeah. Okay.
But that's it. That is it for this problem. That took way too long. Oh wait, I should wait for you guys. Sorry.
Just because
Okay.
of the proof, that's why.
Yeah. Like, but the thing is, like, this is how these problems are gonna go if you do it the long way. Like, you're gonna have to do all this stuff.
Is this a long way?
Kind of. The long way. This is like 40% of the long way.
Yeah.
I might send you my PDF of my homework because, like legit, when I did the problems, it'd take like an hour and a half or 2 hours. If you do it the long way. If you do the long way, if you do the shortcuts using the oscillations and the damp responses, then you don't have to do all that.
Okay. Wait, what's IL infinity equal to there?
What's
I
what?
can't see it. What's IL of infinity equal to? I can't see it.
You said it's 0.
Oh, 0. Oops. Okay. That's shoot.
All right. Okay, it's 10. Okay, so maybe I'll try to force a shake. All right, so that's it. You got those things again. You could try. I don't know if I want to do it again for this. Well, this only asks to do the 0 minus 0 plus. This was not bad. This would you do the steady state set. Let me see. Maybe I don't have to show how to do it.
This one was easier.
Yeah, this one's easier because you know off this, you already know that you just have to look for VC of 0 minus because it equals to VC of 0 plus. And you have to look for IL 0 minus because it'll equal to IL 0 plus.
Yeah, it's just because of the weird differentials for the last one that took forever.
Yeah, because exactly. It asked for the IDT, which is what she did here. See? So she solved it for, let's see. Yeah, so this is the steady state. Right here's the steady state. They're redrawing it, and then she solved for VC of 0 minus, which is this, which would just be, oh, this is shorted, which is why she doesn't draw the resistor. Because the resistor would normally be here, but because of the inductor shorting it, it gets ignored basically. So she just draws the state of the circuit like this. But anyway, so that means that this VC of 0 minus is now in parallel with this guy. So if you find that, you be set. I think she does it through voltage division, no? Oh no, you just do Ohm's law. My bad. You do Ohm's law. You do Ohm's law for this current, solve for it, and you just do 4 times that current. This is what she does here. This is the Ohm's law. She gets the current, which also represents an IL 0 minus because IL 0 minus is right here. That's IL 0 minus right here. So we do Ohm's law, you automatically get it already. So you get 2 things at the same time. So you get this, and then you can immediately plug it into here, which is what she does here, and you get your VL 0 minus. So that's that. If you do the infinity, then you're just gonna do this. You're gonna flip the switch. Switch is off. The 4 ohm resistor is gone, but everything again is the same. So you have the inductor here again. But the thing is, so since the switch is flipped off, normally you would have here the VC. But it's basically this because it's in parallel. You know what I mean? Meaning that, see, since this is open, no current flows. So IL 0 is minus, and then this part is in parallel with this now because this is dead because no current. So it's just VC. This is VC of infinity over here, which is equal to 18 volts. Yeah?
Yeah.
Does that make sense?
Yeah.
This is much easier to do. I just don't want to redraw it again.
Okay. That's just like in the inductor and the capacitor pretty much separated for majority of the circuit stuff.
Yeah, it's separated. But sometimes like how you saw before that the inductor's current could affect the capacitor. You see here, this inductor's current is also flowing through the capacitor here. So I used that same current. That's why I'm looking at the problem. I'm a bit tired, so like it just flew over my head. I was like, I wonder how I got it.
You're good.
But that's it. If you have
Okay.
questions on this, I mean, I can show you, but I think you guys should be able to do this one on your own. Now the part. All right. Okay. A few things I need to cover about this will be differential equations. So, when you have a second order differential equations, you will have 2 initial values. For first order, you only had 1 initial value. That initial value was the I0 minuses you were looking for and the V0 minuses you were looking for.
Yeah.
That not initial values, initial conditions. That's a better word for it. Those are the initial conditions you're looking for first order. But when you have a second order, you need 2 initial conditions. It will be the 0 minuses you've been looking for the entire time, but it'll also be the differentials, which is why she was teaching you how to do it. There'll be the DI 0 plus or some DV 0 plus. It'll depend on the type of problem you're doing. But for differentials, second order, why is there just an A here? Second order differentials, you need two initial values. So this is just arbitrary. So it could be a v or my bad, some v0 minus or some I of 0 minus, something like that. This will be the first one. I'm just giving you a very quick gist of what it looks like. First initial. And then your second initial will come from something like this. So it's going to be like some dv of 0 minus dt or some di 0 minus dt. If you look at what's happening right now, that's fine. I'm just giving a quick run through. Second initial. That's how that works. That's how these hyperpolars will work. So, we have a bunch of proofs. I sadly won't go over them, but the format of a differential here is kind of this here. You're gonna call this will be called some some alpha, and this will be some w. You probably already seen them. That is the format of the second order differential for a circuit. That's the format or the constants you say. Let's see. Okay, we'll see. Okay, here's the proofs. I don't want to go through every single piece of it, but just like this, like having the general form, just helps to like write down, because after that, you're.
I was gonna say the I equals AE to the ST. Where did she pull that from? To be honest, I have no idea.
That's like when you do the auxiliary equation in differential equations, like for example, if you have y double prime plus p of x y prime plus qt, I just call it qt, dy equals 0. You apply the quadratic formula, right? And you get your roots. Do you remember when you write down the equation? It'll be y equals c1 e to the first root, x1t plus c2e x2 of t. That's where that comes from. Hence, that's what the roots are here. That's what I like. It's a differentials. But if they, there's more proofs. I might show you in my notes. It'll be easier to look at. She does the characteristic equation, so she does the auxiliary here, which is what she's doing here. This is the quadratic formula. And then she gets t. So these are the alpha I was talking about, and this is the omega I was talking about. Yeah. And then if... we're skipping a little bit. So yes. So here's the format I already showed you. But the thing is that changes this is that you can have, remember, in differential equations, when you could have linear solutions, non-repeating solutions. So you have a linear solution for each one. For example, let's say you got like x1 equals 3, and then you got, what would it be? It'll be like 3 of x. I kind of forget how from there and then. So let's say some 3 of x. No, because they're roots. Yeah. So you get x1 equals 3, and then x2 equals 2, right? When you write down the formula, it'll be a1 e to the 3 t. My bad. 3t, right? Plus a2 e to the 2t. But the thing is, if you got to say repeated, something like this, after your quadratic formula, that changes things. So you're going to get a1e to the 3t, but then you're going to have plus a2, some variable. In this case, ours is t, plus a2t e to the 3t. Now, if you got imaginary, for example, you got x is equal to 3 plus or minus, let's say negative 4, right? Your alpha is 3, your omega is 4. So when you write down this solution, get y equals like this. So it'll be a to the cosine of 4t, this would be a1, plus a2 sine to the 4t times e to the 3t. Remember that? But that's where these things are coming from. That reasoning. So if you're this is because of the square root. And your square root, if you have does she show it? Wait, no way. Wait, is it just this? Yes, it's just this. So these are the solutions. If this alpha is bigger than this omega, which is here, you have an overdamped case. If they're the same, that means it's repeated. So you have this, the critically damped. And if this is bigger, you can already see you're gonna have an imaginary solution. So you're gonna have J. So you're gonna have a cosine for the underdamped, which you can see here. See? If alpha is bigger, you get the linear solution. Linear factor solution. You get this. If they're the same, if these are the same, which is just saying this, you get the should get repeated. Where's the repeated? Shouldn't I write down the repeated? There you go. The repeated. This is the repeated solution. You have the t in there. And then if the w is bigger, you would get the imaginary. Oh my god, her notes are so. Here you go. The w is bigger. For example, here you get the imaginary, which is this here, and you get the complex, blah blah blah. But you can basically get the. Oh, is she doing the proof? She is. This is Euler's identity, by the way. It's just saying this. If you want to know. I don't know why she uses that, but it's a to the j theta, which is equals to. Oh, she has it there. What am I talking about? But yeah, she uses Euler's identity to prove this because she has it here. You just plug it in. Oh my god, this fucking proof is crazy. But basically, you just get the cosine. Where is it? You get this. This is the formula. This is the formula you need when the w is bigger. And one more thing. No, that's it. I think I just flew by. Yeah, that is it. So here, I'm gonna go back, and then I'm gonna make you guys write down the stuff you need to write. So you have 3 cases. Which are these? This is important. These are the 3 cases you have. Your alpha and your omega are calculated via this here and here. That's alpha omega, right? Depending which one is bigger, for example, if you have alpha is bigger than omega, you get the Oberdam case, which is this formula here. You immediately you can write it out. Your solution S and S2 would be here. That's that. Now, if you get the where alpha and omega are the same, you would get the where is it? You get this one. And now if you get omega's bigger, which is again, sorry, I need to make sure. Yeah, they're the same. Unless you write something here. Yeah, if you get this where this omega is bigger, you get the cosine case. So you just skip and you just write this down here. And in the formulas, you already have where the alphas are placed and where the omegas are placed. So this will be the equation of whatever you're looking for. This is the shortcut method. Meaning you don't have to do differentials, but you do have to solve for. You still have to solve for the conditions, which I'll show. But those are the formulas you should be looking out for. For example, here. Did she just write the roots? Oh, she just write the roots. Okay. So he applies the formula. So look, this is alpha. So write this down. This is omega. Okay. Look, this only applies for series RLC circuits. This is a series RLC circuit. Okay. So I immediately use the formula. My R would be the resistor in question, which is 40, which is this guy. 40. The inductor now, or inductance, would just be, again, the inductance of this, which is 4. So this would be 2 times 4, which is boom. You have your alpha. Now for your omega, it's just 1 over the square root of the inductance and the capacitance. Those are given already. Boom, boom. Right up here. And she's just writing the characteristic equation. But look, you have the Oberdam case. This alpha is bigger than this omega. So if you want to solve for it, the S1s, I want to take a screenshot of those S1s actually. One sec. Let me get them. There you go. A screenshot of this. Because that's where these S1s are coming from. But so yeah, I just highly recommend just like going through going through the sizes and making a formula sheet. I'll show you mine so you guys can get in again. But look, so these are the S's. So look, you have the S you got here, -5, and then you square, and this is the omega you got here, which is this. You get this, and that's the S1, and S2 is the same thing, but with just the minus replaced here. So now when you write down the formula, since you have the Oberdam case, that means your formula, which is this one, yeah, your formula is this. So we're going to use that. It's going to be A1E S12 and AE S2T. That's what she does right here. See? It's not too bad if you do the formulas, right? So that's how you do the shortcut method. Let's see if she does an actual problem. Sure. Oh, one more thing. You would write these what do I call them? You would use these shortcuts at the transient state, like, which is what we've been doing the entire time. But yeah, you use them at the transient state. You don't use them at like steady states because these formulas only work when the circuit's in transient state.
Only transient state for
Yes,
everything.
please. Yes, yes,
Okay,
yes, yes.
Transient state.
Which is what she does here. So she for this state, she solves for she solves for the IL0 minus. No, I'll do it with the other problems. I'll just go over these real fast because you have the notes here. She solves for the IL0 minus because at the switch is going to be connected down. So we're going to have, this is the switch here. But the thing is the capacitor is going to be open circuit. So this is gone. So this capacitor is going to be like this, which kills this entire branch off. No current's going to flow through here. And then it's going to be shorted, which is right here. This is the inductor shorted over here. And now all you have to really solve for is just this current. So you do Ohm's law really fast. It's going to be 6 plus 10 over 6, 10 over 4 plus 6, which gives you 1. And then for the V0 minus, which would have been, wait, this is why did she not write that? This is IL0 minus. IL0 minus. The VC of 0 minus would be, where's the switch? Oh, wait. Find the current IT of the circuit. Oh, for the resistor. Fuck. My bad. This is I. So that means this is for the resistor. So R, VR. So yes, so once you know the current, you just multiply the resistance by the current, which gives you the voltage of it. And then, why is she solves for the DI0 plus and the VL0? 0 plus. The VL, oh, she relates it. Okay, wait, I gotta look for the formula again. So this,
She
the
did a thing
VL,
in class for this question, but there's another way to do it for, I think we're having trouble finding the voltage across the capacitor, but there's another way to do it too.
for this part, is that why she didn't solve it here? She just writes 0?
Maybe, I don't know. I think it was a later part. I'll point it out when I remember it and see
Okay.
it.
Okay, it's okay. VLT is equal to L DI L 0 over dt. The voltage of the inductor should be 0 because it would equal to, we're going to get, real quick, we're going to get 10 minus 10 volts plus 4. By the way, it's just going to be 4 times 1 because of this current. So I'm going to get plus 4 times 1 plus 6 times 1 plus the VL. Yeah, it does equal to 0. Because look, these cancel out with this, and this VL is equal to 0, which is why she writes this. Just FYI.
Say one more time, please.
Yeah, so she does KVL around this loop. It's like what we did with that first problem. She does KVL. Oh my god. Sorry. She does KVL here.
Sure.
And then you get the minus 10, the plus 4, which is this. We know the current already because of this 1A, because we did the Ohm's law before. So it's going to be plus 4.
Around the entire loop, and it's open there.
Yeah, so it's 4, 6, and then this is the VL over here.
Mm-hmm.
So it's just plus VL, but these cancel out already. So VL is 0.
Cool.
That's what she does. So now t equals 0, the switch is open, which is when you apply the shortcuts you guys learned. So she already writes on the
second the switch closes or opens or whatever.
or yeah, it does something. The
Yeah.
second the switch. So that's when she applies that. So now we have a picture of the formulas. She write them. So we know that 2RL. Oh, where's the Should I write down a W? She does not. So W is equal to, I'll write it here, equals 1 over the square root of L times C. That's what that comes from. I don't know why she doesn't write that part down. But the L we already know was 0.5, the C is 0.002. So this comes from the 1 over square root of 0.02 times 0.5, which should equal to 10 if her math is right. Which I guess I'll check. Zero 0.02 times 0.5. Yeah, it's 10. Okay, and then this just comes from the fact that the resistor in series, because since this switch is flipped up, you're doing this. The resistor in series would be
9.
9. Yeah. Thank you. Yeah, 9. So you plug in 9 here, and then divide by 2L, which I'll check again. 9. This will be 9 over 2 times 0.5. Oh yeah, which is 1/2. 9 over 1 equals 9. There you go. That's where that comes from. So now you know you have a underdamp. This is your W, and it's bigger than 9. So you have this case. So now you use this formula here. And then you plug these in. Well, I'll just go back to up here. That's the formula you use. Oh, I'm using the wrong mouse.
And this is a source-free circuit because the source is no longer a part of the circuit, so it's just LRC.
Yeah, exactly. It's in series too. Series LRC.
Yes, series LRC.
Why does it do that? I'll take a screenshot.
What happens if one part's in series and one part's in parallel?
Oh man, that's where you have to do the long way. Yeah,
Oh.
I have a problem where you didn't have one of the cases, and that shit was fuck. I'll upload my work on the Discord. You guys can just see it.
Yes, please.
And I prove a lot of work, but the thing is, I don't do any shortcuts, any of them. So learn to apply the shortcuts. Oh no, I can send you the solutions. All the solutions do shortcut methods. I don't. I do differential methods. It's gonna be a bit hard to follow, but do what you're doing right now. Do the shortcut method. Check if your answer's right, and then look at my differential method and see if you can replicate it. But I try to be very like organized, much more organized than what I'm doing right now, because this shit's ass. But I'll upload after. Where's it going? Where's my formulas, man? Oh, it's going there. Fuck. I just want you guys to see where these numbers are coming from. Okay. So this WD that she's calculating here comes from this formula here. W theta, which would be what you got before. This 10 equals W theta. So you plug it into here. This alpha you already know, which comes from here. You plug it into here. Now you have WD. So here's the part I was talking about, where you have to know the initial conditions, because you're gonna need 2 to solve for this. The thing is, so this formula writes down the current for with 2. Wait, one sec. What was the difference of them? Like, oh, we'd have to solve for them. Okay, this we don't have to do anything because we don't have to solve for A1 and A2. If we have to solve for it, we're gonna need 2 equations. We're gonna use this one as the first initial, and then we're gonna find di t dt. So we derive this and get 2 equations, because then we can use system of equations to solve for the A1s and A2s. Because you can't just leave A1s and A2s. Just FYI. That's what we didn't do for this problem. But for this problem, we're actually doing it. So I don't want to derive this, but okay. Let me first finish what I was saying. So we have the WD, which is what we need. So now we go back and get the initial conditions we had. So we know that at t equals 0, I0 was 1a, which is here. Remember that this also equals to I of 0. And we're going to use t equals 0 as our placeholder of initial conditions. If you remember the q, most of your initial conditions were at 0. Just FYI. Not 0 minus, or 0 plus, but 0. So that's what we're going to do. We're going to use this guy to solve for our constants. So we plug it into the formula that we have here. The formula being this over here. We're going to minus alpha was just, where is it? 9. Did she plug it in? Oh, because we plug in for t. So we're plugging t for 0 here. Sorry. Here, here, and here. And the WDT, oh, she has it. Okay, she has it. So we're going to get here E0, we get this formula, basically. And then we solve for, well, this is just 0, right? Cosine of 0 is 1. So we just get b1 is equal to this. So we have one constant now. That's what happens here. So now we have to solve for the other one. So what we do is we derive it, which we'll see doing here, and then you get this whole chunk of mess, which I'll let you guys solve for because I'm not doing that. But basically, you're deriving this here. But you could plug in the, see how, I don't know if she keeps this here. Maybe, does she give you a shortcut method? No, she does not. But you can plug in the alpha here and the WTs you know. So the minus alpha would just be minus, where's the alpha you got? Minus 9. Let me write this here. So the alpha is equal to 9. The W you know is equal to, oh no, it'll be the WD. In the formula you plug in WD. So the WDT that you saw for earlier will be 4.36. And you can plug those in for here. So this is the alpha, and then you plug the WDT. And basically you would have a formula. Let me just write it out. So you would have I of t equal to E minus, I think it was 9, minus 9 of t, A1. Oh, I don't have the full formula. Where is it? A1 cosine, yeah. Be A1 cosine the WT, which is 4 point, where is it? 4.36. WT 4.36 of t plus A2 sine 4.36 of t. And then you derive this. You derive this, which would just reduce to this here, actually. This would reduce it to the minus alpha and the B2 you had. So then to get the IDT, just plug in the V2s. No, not plug in the V2. You would set it equal to what the IDT was, which was, where was it? Where was it? Where was it? Where was it? Oh, which is 0. See? So I'm using two initial conditions. So the IDT I got for before, and the ILs and VLs minuses I got for. So since this is equal to 0, I go over here. Remember, this is the I of dt of 0. So I plug in, this is supposed to be 0. I plug in 0 here, and then I solve for my constant v2, which would just be the alpha, which is, this is 9. 9 plus b2, this is 4.36. So v2 would just equal to 0. b2 would just be equal to minus 9 divided by 4.36, which I think should be, yeah, what? It's not 4.36. What is WD? Wait. I messed up. It's not 0. Why is it not 0? How the wait, how did she get 30? Wait, when was Wait, Trishan, is this the part you're talking about? How did she get 30?
30 right there. Because are my notes. My notes are better. Okay. 30 amps there.
Yeah, where'd she get the minus 30 from? Oh wait, what's the alpha? The
Okay.
alpha is,
Yeah, she kind of put it in a weird spot, but she did di of 0 over dt is equal to
yeah.
-1 over L times RIO plus VO. She did some weird formula that was like in the back or in one of the sections to find the IO. I think I did something else though. Oh, I missed my mini notebook. I think what was it? Here. I don't know if I can point it out or not. Let me see if I can find it.
Okay. Wait.
Lectures. There we go. She kind of put it in a weird spot. I think it's in there somewhere though. This here we go. Can you see my screen or no?
Mhm.
Okay. She used this
What?
to find the amps per second. They're right there. Just that general formula for it.
That's just. Wait, so it would be negative. What is ours? So it'll be -1 over 0.5, right? Times the current, which is 1, no? Times the resistance,
Oh.
which is.
She did this on the whiteboard now. I remember. She did not include it in her notes. She's like,
Oh, it
write
should
it
be
down or you're done for.
3 times. Wait, I'll do it right now. 3 times
Yeah.
delete times 1 plus the voltage of the capacitor, which would be 6.
Got a couple brats in there if you want.
Wait, what was it? She got -30. I got -18. Wait, am I doing wrong? The resistance is 3. No, am I tripping? Oh, it's fucking 9. Oh, I got it. Right? Should be. Yeah, I got it. -30. Okay, wait.
Figure it out. Let me
So
know.
that means that.
Thank you though.
Mhm. Okay, wait. She does KBL. Okay, basically what that formula is doing KBL here.
KBL
But
there.
yeah.
That's what I
Oh,
did. No, that's what I was talking
fuck.
about. Yeah.
Yes, the switch is flipped here, so you will solve for this. Oh my god, I messed up
Yeah.
again. So
No.
you would find the you have to find the condition of. The thing is, she doesn't write zero pluses anywhere. So I'm trying to like remember to yeah. She just writes di of dt, and I'm trying to remember through her notes like what that means. Or like yeah. Anywho, you would do since the switch is flipped up, you just do KBO here. So you get, and it's gonna be the
Yeah,
same current
you can just
that we
solve for
saw
the
for
current like
before.
that.
Yeah.
Yeah.
So should I write it? What do you guys think?
Yeah, go ahead. I mean, this was not in the lecture notes. I was gonna email her a formula I did, then I just forgot. I left it in my small notebook. It's at a different house.
I see. So it's gonna be +3 times the current we got before, which would be I. Let me see what I called it. We called it okay. IR 0 minus. We're gonna use that. It's gonna be IR 0 minus plus no minus, I guess. Minus this voltage minus V of C. And then it's going to be +6 times IR of 0 minus 0, 0 plus VL equals 0. So we know the formula for VL is equal to L di dt. Or got a whole ass survey. Yeah, di dt. So this formula becomes 3 times 1 minus VC, which we already know, which is 6 volts. Wait. Hey, yo. What am I doing wrong? No. Fucking, I messed up again. No. Transient state is when the switch is fucking flipped down. My god. So it's gonna be this. It's gonna be this. The switch isn't flipped up just yet, so it's gonna be what the fuck? It's gonna be minus 10 volts plus 4 times the IR of 0 minus we got plus 6 times the IR of 0 minus we got plus the V of L equals 0. So this becomes minus 10. No, I'm gonna get 0. No. What did I do? Wait, let me look at my calculator. Let you had it.
How are you doing? You're doing KVL, right?
This is wrong. This is what I did before. You had to do it at
Mm.
the 0 part.
Okay. And also, I think when I tried to do this in my weird way or whatever, she said that the voltage signs of the capacitor get flipped.
Get flipped, really.
Yeah.
Circuit enters
Oh.
transient state. Wait, so we get plus 3 times R L 0 minus plus V of C. Plus V of C. Wait, what was the capacitor's voltage before? Does the capacitor even have a voltage?
Yeah, it should have a voltage. Should be fully charged, right? Oh,
At
yeah.
when this switches. Oh my
And the switch
god.
is flipped. Yeah.
Oh, we didn't solve for it. We had to solve. Why? What the?
Oh.
Oh my god, my. It's software here.
It's 6 volts. If you're wondering, I think it was
Is it
just
6?
yeah, it was 6 volts across the capacitor when fully charged.
But wait.
Or
My god. Yeah, because this will be opened like this.
parallel with the 6 ohm resistor.
Like
Yeah.
yes.
Should just be 6 volts then.
Yes. Thank you.
Yeah.
Okay. This is sloppy, but I'm just gonna try to get this through this problem. And tomorrow we can do more problems that are neater.
Ooh.
Plus, so this will be that. So I have the plus 3, I have the plus PC, and then I have the plus 6 times R's or minus plus the VL. Because 0. So we know that VL is equal to L di dt. Correct? Yes. So this is going to be 3 times 1 plus VC, which you told me was 6 volts, plus 6 plus LDI of 0 dt equals 0. So I add these all up. So I get 12 plus 19. So I get di 0 dt equals to, right? 12, no, 15. 15? Yeah, I got it. Divided by, I know this is negative. Divided by L, which is 0.5, which just doubles it, which gives you the 30 amps. Yeah.
Yep.
Fucking hell. Tomorrow we do this again.
Yeah.
My brain is cooked. So I'm just making so many
Yeah,
errors.
you're good.
Okay, so that's where she gets this 30. So you can do it using the formula that Tristan just showed us. Or you can do it what I just did now. Thing is, when you do it this way, you're going to have to do it at the transient state, which is only going to be counted for this loop. This V over here, we didn't solve for because we ignored it because we just wanted the I. But this V is over here. That's that V, which would be 6 because it's in parallel with this. But that's how we got that. Anywho, this will be equal to 30 now, which is the IDT. This is what you solve for, and then you solve for V2, and then you get this. So you get the last constant you need, and then you go back to this problem right here. This over here. So now you get I of t as your final one, e negative 9t. This would be what's b1 1. So you get 1 cosine 4.36t minus 4.82 sine of 4.36t. And that's your final answer. Again, I'll do this one more time. Oh, that was the last slide too. Okay, I'll do it again tomorrow. One more problem. But I want to show you guys. I can give you my notes for the problems or the formulas. I have them like neater here. This explains like the proofs and whatnot, like the different cases. So you have the overdamp here, you have the critically damped, and then you have the underdamped. And then this is me explaining the underdamped case, but here's the Sears RSC. I explained the proof for it. I explained the constants you'll be using. So yeah, see, I have here the constants that you're gonna solve for. That's your alpha, and that's your omega. I also have the parallel here. We don't have to worry about that. We'll cover that tomorrow. But for this, Off this, you go back here, and then you have the cases. So here are the cases. So this is your S1, so your S2. And then for critically damped, you have S1, S2 is equals to that, negative alpha. And then for the overdamped cases, these are your S1 as S2s. You gotta remember your general, do I write it? Here. These are your general ways you write down the formulas. For that. For the S, and then here's the general ways you write those down for the critically damped. And then here's the general ways you write down the, where is it? Where is it? The critically damped. As you can see, there's a derivative she does. This is the derivative she does in class, but like she really like skims over. But just know that this is here's the general formula for that. So I have them here. I don't know if you guys want these notes.
Give.
But yeah. Okay, I'll provide it. But that's about it. I wanted to do the practice problems, but
Okay.
it's 10:44. I'll
Yeah.
upload my homework. So these practice problems I do in my homework. So you're gonna see I did this one doing the long method, but here's the solution using the shortcut you guys know. There's that.
Oh, sweet.
And then this I also did this problem using the long method, but also here's the solution with the shortcut method.
Okay.
And I also make note that but that's about it. I think oh God, so much. My head hurts. I don't think I did a good job explaining second order, but I'll do a better job tomorrow.
I got a general idea of it at least. I wouldn't
Okay.
commit. It's
That's
just like
what
the
matters, yeah.
differential stuff. Like it's messy. That's it.
Yeah, I need a tomorrow. I'm gonna make a more concise step, like how I did with the zero. Look at circuit T equals 0, blah blah blah, so you guys
Okay.
don't get lost.
Yeah.
Well, that's all I got for you guys.
Anything's appreciated, of course. That we always appreciate all this.
Thank you.
Mm,
Well, that's all I got for you guys. That's all I need.
okay.
I'll be uploading everything,
Thank you.
my
Yeah.
formulas and the homework, so you guys can look at it.
Will there be another time when we can go over op amps at all? Because people have questions about that. People being me.
Really?
And Matthew. Yeah.
Let's see how tomorrow's what, Thursday? We still have Friday, right? So we'll see how tomorrow goes.
I mean, there's
Hopefully
also the week because the test is actually on Thursday, the week we come back. So, if that works for you, if it doesn't, then it doesn't.
Let's see. Because
Okay.
I have an exam too.
Yeah, that makes sense. That's fair.
But yeah, I'll let you guys know. I'll keep you guys updated if we can do more sessions.
Good. Thank you.
Of course.
Everything is a
Thank you,
just
Isaac.
Don't make sure to overextend yourself.
Yeah. What he
Thanks,
said.
Patrick.
He said
Thank you.
No, you can hear. What am I talking about? Yeah. Thank you.
No problemo. All right. You guys get some rest. I'll be uploading everything it'll take like 10 minutes for everything to be uploaded.
Gotcha.
I'll let you know. I'm
Gotcha. See you tomorrow.
Bye, Leon. Have a good night.
I'll
I didn't hear him. What did you say, Tristan?
see how it actually processed later, but
He's saying he thinks the recording went well. He'll see how it processes later. But
Yeah. Okay, sure. Next time we should just do snippets of just only the work problems or something like that. I don't know.
Probably whatever.
Yeah, like
That's
problem
how it works.
1.
Yeah, problem
Something.
1, record, and then finish problem 1.
I like to have all the information, even if it is
Oh.
not always useful.
Oh, okay.
at least this way nothing's cut off weirdly in case we're not looking at the problem.
Yeah, he's saying
we're still talking
this,
about
at
it.
least there's nothing cut off weirdly, in
I
case
see.
we're not looking at the problem, but we're
That's
still
cool.
talking about it.
Fair enough.
Yeah.
Well,
Where's it
you're
going to be
recording.
posted?
I don't
Like a
care. I'll
drive
sort through all the stuff.
For YouTube.
Yeah.
I'll
That's
upload
a
it
question.
on YouTube.
He
and
said
then
he'll
I'll just
upload it on
post
YouTube.
Okay.
Oh, it could be divided in chapters then.
You
Like
could
a
if you
little
wanted to, yeah.
section.
You want me
The
to do
timestamps.
it in divided
Yeah.
chapter by chapter?
That's great.
I can.
There could just be timestamps. That works.
You just said put timestamps.
Like the whole vid.
If we rewatch it anyways, just put timestamps as you're watching or something. I don't know. That's fine. We'll figure it out.
Yeah, that's true. Skip ahead. Okay, good night, everyone.
Good night, y'all.